Well, hello, dear friends. So in this lesson, we're going to examine the answers to these questions. What is machine learning? What are some of the terms used in machine learning? But alas, before we go digging into the details of machine learning, we're going to go through a bit of a history lesson. All right? So we'll get started. Machine learning. It sounds like it's a relatively new concept, but it was defined way back in 1959 by Arthur Samuel. By definition, machine learning is the workspace that gives computers the ability to learn without being programmed openly. Professor Samuel was an employee of artificial intelligence at IBM, and he developed a program that could play chess better than a person. Now, artificial intelligence, which became especially popular by the 1980s, continued to be developed to make reliable predictions in more specific areas after it was seen to be successful in certain other areas. So basically, machine learning was developed in the 2000s. So the system, which can interact naturally with people as part of cognitive science, it's gained the ability to find solutions to complex problems thanks to its ability to predict. Yes, my dear friends, let's get into some of the details now. So what is machine learning? Machine learning is a data analytics technique, getting computers to learn and also act like a human. Machine learning algorithms use computational methods to learn by feeding data and information. And it also is known as a field of data analytics to make predictions depending on trends and insights into the data. Machine learning algorithms use statistical tools to find important connections in large amounts of data. Now, the data we're talking about here covers many things like numbers, words, images, as well as clicks. So if this data can be stored digitally, it can be fed into a machine learning algorithm. So in short, the main basis of machine learning is to create algorithms that can process its data and predict the result using statistical analysis. The new data obtained during this process continues to be learned and used to update and become better with its results. Machine learning, which can analyze data without any human intervention, it offers the best estimates, and it's also used in many corporate applications. But by the same token, it also helps many professions with the opportunities it'll provide. Machine learning is becoming an increasingly needed application in today's world, with its functions like ease of data analysis and giving the top estimates, defining abnormalities, and solving problems. Machine learning algorithms are used in an extensive variety of applications, such as recommendation engines, customer churn, new pricing models, email spam filtering, material and stock estimates, pattern and image recognition, predictive inventory planning, purchasing trends, credit scoring, and sure, the list could go on. So in this lesson, gave you a little bit of an introduction. We've learned what machine learning is and how it can be used, where it is used typically. So we're going to take a brief pause here, and we'll come back into the next lesson. Well, hello, dear friends. So in this lesson, we're going to examine the terminology of machine learning used in the machine learning world, and consequently, the upcoming lessons throughout this course. All right, so let's get started. Observations. So observations is a piece of data used to learn for the model. Each row in a data set represents an observation. For example, each email could be an observation. Features. Features represents a measurable piece of data that can be used for analysis. For example, name, age, gender, size, fare, date, etc. Features are also sometimes referred to as variables or attributes. Each column, except the label column in a data set, is called a feature. Labels. Now, the label, it's often called the target column. This is the thing we're predicting. So briefly, the features are input and the label or target is the output. For example, churn, spam or not spam, price of a house, this kind of thing. All right, so this picture here demonstrates a very simple data set. So in this data set, each row is an observation. Name, age, gender columns are the features of the data. And here's the churn column. This contains the labels of the data. Now, what about the training and test data? Training data is a subset of the full data set to train a model. Test data is a subset of the full data set to test a model. So to summarize, our data is divided into two: training data and testing data. Then we use our training data to train our model. All right, so now it's time to test the model. And yes, indeed, we have tested our data according to the trained model. So then the next step would be evaluate the accuracy of the result that we have achieved. Now, since we haven't learned the metrics, we're going to end the lesson here. All right, dear friends, so in this lesson, we've talked about machine learning and the terms that we've used in machine learning. I hope to see you in the next lesson. Until then, have a nice day. Hello, dear friends. So in this lesson, we're going to learn the difference between classification and regression. So let's get started. Supervised learning is the most common type of machine learning because it is much easier to train a machine to learn with labeled data than with unlabeled data. So in other words, depending upon what we want to predict, supervised learning is used to solve two types of problems: regression and classification. So now let's consider them separately and start with classification first. So classification is simply a way to distribute data between the various classes defined on a data set. Classification algorithms learn this distribution form from the given training set and then try to classify correctly. In the classification, the group membership of the problem is defined. The data is categorized under different labels according to some parameters, and then the labels are estimated for the data. So if there are two classes, this is called binary classification. If there are more than two classes, it's known as multi-class classification. All right, so now let's talk about regression. Regression is the prediction of the behavior of a random variable using a model. For example, let us have a model trained with a data set. So with this model, we can predict a value that we want to learn or another value that corresponds to a value. This process is called regression in statistical science. Basically, regression calls a relationship between two or more variables. So the task of measuring the level and scope of this relationship is called regression analysis. It's necessary to obtain the relationship between parameters as a function. Now, parameters can be independent or interdependent of each other. So, my friends, that's the evaluation of regression and classification. So let's dig into some of the differences now. So some of the main differences between classification and regression. The main difference between classification and regression is while a categorical variable tries to estimate in classification, for example, patient or not patient, 0, 1, a continuous value is attempted at estimation in regression, for example, car or house prices. While classification predicts unordered data, regression predicts sequential data. Now, another difference is evaluating the performance of each. So while classification is evaluated by measuring techniques such as accuracy and precision, a regression can be evaluated using mean square errors. All right, so there you go, regression and classification. In the next lesson, we're going to learn about the criteria used to evaluate them and how to interpret all of that. So until then, have a nice day. Well, hello, my dear friends. So in this lesson, we're going to learn performance classification of classification error metrics. All right, let's get started. So what are these classification metrics and how are we going to be using them? Now, the key classification metrics that we should understand are our accuracy, recall, precision, and F1 score. So first off, we should understand the reasoning behind these metrics, and also that'll give us a clue as to how they actually work in real life. So typically in any classification task, your model can achieve two results. Either your model was correct in its prediction or your model was incorrect in its prediction. And pretty much all classification metrics originate with this idea. Fortunately, incorrect versus correct also expands to situations where you have multiple classes, such as trying to predict categories of more than two. For example, you have categories A, B, C, D. Well, you may be correct in guessing the correct category or wrong in guessing the correct category, right? All right, so let's continue on with the metrics. So this is simply known as binary classification, all right, which just means binary, really. there are only two available classes, yes? Either class 0 or class 1. So this idea is going to expand through multiple classes as well. But for our purposes, and to simplify it, let's just imagine a binary classification situation. So in our example, we'll try to guess whether an image is a lion or a tiger. Now, as this is a supervised learning problem, the first place we need to do is build or train a model on some training data. This means we're going to have images where a person has gone before and has been tagged as a lion or a tiger. Then we'll test this model on test data. So we're going to show new images that the model hasn't seen before. Take the model estimate and then compare the results of the model estimate with the correct answer that we already know. Hence, when we have model predictions from X test data, we compare it with actual Y values. So let's actually diagram this process out. Now, supposing that we have already trained our model on some training data, and now is the time to really evaluate the performance of the models. So this is where our test data set comes in. All right, so we get a test image from where we will tag the X test, X meaning feature. So the actual image itself is a feature, and there is a corresponding correct tag from this test set and test Y. So we have the X feature or image and this test image, and also we have the correct label from test Y. And in this case, we can see that this image is an image of a lion. So we'll just feed the features. The image in this case is already trained to our model. And then the model is going to make some prediction. So the model predicts that this is a lion. And then what we do is we compare the prediction to the correct label. So this lion equals lion, and it's correct in this case. But maybe it guessed this image was a tiger. And in this case, this comparison with the correct label would be wrong. And these are actually just two cases. Of course, you're either right or you're wrong, correct or incorrect. So then we repeat the process for all images in our X test data. And then eventually, we'll have the count of correct matches and the calculation of incorrect matches. And the main difference that we have to make here is that not all false or correct matches are of equal value in the real world. So why don't we focus a little bit more on what we mean by all this? So in the real world, a single measurement won't tell the whole story. To understand it all, let's bring back 4 metrics that we mentioned and see how they actually calculate. So we can arrange our predicted values by comparing them with real values and what's known as the confusion matrix. So we'll touch upon the confusion matrix a little bit later on, but let's talk about accuracy first. Accuracy is one of the most common classification criteria. Fortunately, it's easy for us to understand. So it's really intuitive what it's measuring, right? So in classification problems, accuracy is obtained by dividing the number of correct predictions made by the number or total number of predictions made. So again, it's the number of correct predictions divided by the total number of predictions. How many guesses will you get correct? And what's the percentage? For example, suppose that the X test set is 100 images and our model correctly predicted 80 images. Well, we've got 80 divided by 100, or 0.8, or 80% accuracy. Right, and the accuracy is really useful when the target classes are well balanced. And what does that mean? Well balanced, well, in our example, this means that the actual tags are represented roughly equally in the data set. But let's imagine that we have what's known as an unbalanced class case. So basically that means that the actual labels themselves are roughly equally represented in the data set. Let's imagine that we have what's known as an unbalanced class situation. So in this case, accuracy is actually not a good metric to use. So let me take you through a little thought experiment. Let's imagine that in this test, we had 99 images of lions and only 1 image of a tiger. Now, if our model was simply a line that just always predicted lion, no matter what the image it saw was, then we would actually get 99% accuracy with this particular test. Because by 99 images are lions and 1 image of a tiger, well, it only missed 1. So you should be aware of the downside of accuracy. And this downside will arise when you really have an unbalanced class situation. So if your classes are roughly balanced, accuracy is a very nice or intuitive method or metric to understand. However, if you have an unstable class, you may find that it starts to represent a problem in this particular case. And that's where these other metrics come in. So again, in this case, you'll want to understand recall and precision. That helps us understand how well it performs in unbalanced classrooms. Recall is the ability of a model to find all relevant cases in a dataset. And the exact definition of recall is the number of what are known as true positives. And we'll focus on that later on when we see the confusion matrix. But it's the number of true positives divided by the number of true positives plus the number of false positives. And precision is the ability of a classification model to identify only the relevant data points, where precision is defined as the number of true positives divided by the number of true positives plus a number of false positives. So often you have a trade-off between recall and precision. While recall expresses the ability to find all the relevant instances in a dataset, precision expresses the proportion of the data points our model says was relevant that actually were relevant. And then there's the F1 score. So this is essentially a combination of the both of them. So in cases where we want to find the optimum mix of sensitivity and recall, we can combine the two metrics using what is known as the F1 score. The F1 score is the harmonic mean of the precision and recall that takes both measurements into account. So this is not just averaging the recording position, you get it? But actually taking their harmonic average. So the reason that we use harmonic average instead of a simple average is that it will penalize extreme values. For example, if you create a classifier that had a precision of 1, meaning essentially perfect precision, and a recall of 0, meaning essentially the worst recall possible, if you were to just take the simple average of this, then it would be 0.5. But the F1 score, because it's taken a harmonic average, we have precision times recall there at the top, which means you get 0 times 1 of the top, and you get an F1 score of 0. So this is really nice because it allows you to punish the extreme differences between precision and recall. So basically it gives you a fair assessment of this trade-off between precision and recall. So we can now view all correctly classified and misclassified images in the form of a confusion matrix as well. All right, so are you ready for the confusion matrix? It looks something like this. So we have the right underlying conditions. This is the correct label, and we can actually think of the situation as positive or negative, such as being a lion or not being a lion. Or it's often used in medical diagnosis, such as the presence or absence of disease. Well, we have the presence of disease, and then we have patterns in which the condition is predicted. You follow? So the forecast is going to be a positive or negative guess. And when it comes to confusion matrices, I think it's easiest to get an intuition first if you think of it as a diagnostic test for some kind of disease to be present in a person. So you run it through your model. For example, a true positive might be that someone actually has that disease, and your model accurately predicts that they have the disease. A true negative is that someone doesn't get the disease, and your model accurately predicts that they don't have the disease. So there are true positives and true negatives, and these are both correct predictions. And then we actually have these two types of false predictions, one false positive and one false negative. If the person does not have the disease, it will be a false positive, and you predict that they do not have it. That is also a positive. Because you're wrongly saying that they're positive for their disease or condition. A false negative is essentially the opposite of that, where this person does have the disease present. So if you report back using your model and your test that it's actually negative, well, they don't actually have this disease. These are sometimes referred to as a type 1 error and a type 2 error. And then, based on these essentially true positives, true negatives, false negatives, and false positives, there are many other metrics that we can calculate. So as we can see, the actual calculation for accuracy in the lower left-hand corner. We can see some here, and that's the sum of the true positives plus the true negatives. Essentially, out of the total population, it is the sum of the correct ones. And there's a bunch of other ones like positive likelihood ratio, false positive rate, true positive rate, prevalence true discovery rate, and many more. But now the main point here to take away is the confusion matrix and the various computed metrics are basically the main ways of comparing the predicted value with the actual value. And what constitutes good metrics actually really depends on the specific situation. All right, so now a very specific question for you. Is that good enough accuracy? Well, it really does depend on your situation and the context of the situation. But now, if you're still confusing the confusion matrix, it's really no problem. Check out the Wikipedia page for it. It's got a really good diagram with all the foremost for all the metrics. So now I want to go back to the first question. Is that a good enough accuracy? And as always, this really depends on the context of the situation you're running your model in. There's no single number I can give to say something like 90% accuracy is good enough for every situation, right? We've already seen the topic in unbalanced classrooms, but there is no really good explanation for what it is with a good enough precision or recall. And we need to think about the context of the situation. So let's rethink the diagnostic model to predict the presence of a disease. So if we have created a model for predicting the presence of disease, the first thing that I want to think about is, are we going to have balanced classes or unbalanced classes? So the presence of disease in the general population is well balanced and is almost unlikely in most cases. There will probably not be a disease in which about half of the population is affected and half the population is not affected. So we can already tell that we're going to have an unbalanced class situation where this means that we're not going to have a precision recall trade-off. Therefore, we should not forget that these models are often used as rapid diagnostic tests that must be done before having a more invasive test. For example, for prostate cancer models, it's very common to do a simple urine test before taking a biopsy because it's much easier to have your urine tested than to do a complete biopsy of the prostate, yeah? So we also need to consider what's at stake. If it's prostate cancer, the risks are actually quite high. So as we mentioned, we often have a precision recall trade-off, which means we have to decide whether the model will focus on correcting false negatives versus false positives. So at the expense of reducing false negatives, we'll likely increase false positives, and vice versa. And it's probably better to try to minimize the number of false negatives at the expense of increasing the number of false positives when you're talking about disease diagnosis. So it goes in the direction of false positives. And why do we actually want to do that? Well, because we want to make sure that we correctly classify as many cases of the disease as possible. Therefore, we are doing our best to reduce false negatives at the expense of increasing false positives, right? Why would we actually want to do that? Well, in fact, we want to make sure that this disease exists, or anyone with prostate cancer in this example, if we're doing a urine test, we want to make sure that all these people exist. The disease will actually go to the next step. That is perhaps a more invasive test, like a biopsy. And remember, this kind usually comes at a cost of increasing those false positives. So we can see for something as important as disease diagnosis, really minimizing those false negatives becomes really important. And pretty much all of this is to say, machine learning is not going to be performed in a vacuum. And these performance metrics don't have some kind of universal truth that applies to all problems. But machine learning is truly a collaborative process where we must always consult experts in the field. For example, in the case of disease diagnosis, we should probably be talking to doctors as far as what our acceptable standards for false negatives versus false positives are. And this is going to change depending on the context of your situation. So just always keep this in mind. For me, it would not be an easy answer to say that this is a good enough accuracy or precision or recall, because it all depends on the context and scope of the situation. All right, so that is I'd say an introduction or a brief overview about how we can evaluate classification models. Of course, the more you evaluate, the more evaluation will be done. So we'll go ahead and we'll move on to the next lecture, because we're going to discuss evaluating regression tasks. All right? So I want to see you there. Well, hello, dear friends. So in this lesson, we're going to learn the error metrics. All right? So let's get started. In general, when a model constantly tries to predict values, it does this as a regression task, as opposed to classification tasks where we try to predict categorical values. Therefore, as we just said, you may have heard some evaluation criteria such as accuracy, recall, or precision. Well, these sort of metrics aren't going to be very useful for regression problems. So it doesn't really make sense to calculate the accuracy or recall of a regression task, because you're actually classifying things. Instead, you're predicting a continuous value. So that means we need new metrics designed for those continuous values. For example, imagine trying to estimate the price of a house based on its features. Well, this would be a regression task. Or it may be trying to predict the country in which a home was located, given its characteristics. Well, that would be a classification task. Okay, so now we're going to focus on how to evaluate this regression task where a tag is continuous and not separate categories. So moving on to discuss the most common evaluation metrics for regression, which are mean absolute error, means squared error, and then root mean square error. So let's begin with the simplest, which happens to be mean absolute error. And, well, perhaps it's the easiest to understand, so let's lay it out. Basically, all you have to do is compare and remember your predictions. So here we're comparing a continuous value because this is a regression task, and we will compare our predictions with the true Y label. For example, compare the actual prediction of the house price with the true house price. And then what we do is just take the difference between the true price minus our predicted price. And you see, that's why we take the absolute value of that. And the reason we take the absolute value is because technically our predictions could be over or under the true value. And since we want averages across all our predictions, we will take that absolute value. Okay, so this is basically the mean absolute error. You just get the differences between your prediction and the true label, and you get the absolute value of that, and then you get the average of all of your predictions. Now, there is an issue with mean absolute error, is it won't punish large errors. So here we have something known as the Anscombe's quartet. And here we can see that we have a wide variety of different distributions of data points. However, the line of best fit for all of these is actually the same. So you see why we want to make sure that we're aware of these kind of situations. So let's take a look at this particular case, for example. So here we have a point that is a big outlier, right? So we want our error metrics to really take these into account. So what we can do is actually use the mean square error, and this is the mean of the squared errors. So what we're doing here is we're going to take the difference between the true value minus our predicted value, and then we're going to square it. And when we actually take this square, as you can guess, that larger errors are noted more than the mean absolute error. So this makes the square error a bit more popular, because you're going to actually penalize your model for those outliers where it's just not suitable. And we don't need to take absolute value anymore, because everything that is square is positive. However, there's an issue that we run into with mean squared error. This is the squaring of the actual label minus its prediction. Actually also squares the units themselves. So, for example, if you're predicting the price of a house, then our error metric with mean absolute error would be in dollars, but with mean squared error, we end up getting an error metric in units of dollars squared. And, well, I haven't checked my bank account today, but I think that's pretty difficult to interpret. So the way that we fix this is with the root means squared error. So essentially, at the end, you just take the square root of your mean squared error. So this then becomes the most popular because it penalizes both larger error values and has the same criteria or the same units as y at the end of the day. Okay, so let's continue the most frequently asked question. Is this root mean square of the error value any good? Well, as always, context is everything. Okay, so now suppose you're implementing some kind of machine learning model and you get a $20 root mean square error. And then you ask me, is this root mean squared error? Well, is it good enough? And again, I got to reply, well, it really does depend on the context of the situation. And you get that, right? Context is everything here. Because if you're predicting the price of a house because it is $20 smaller than the average price of a house, root mean squared error, $20 error, well, that's really good, yeah? However, if your machine learning model needs to estimate the price of a chewing gum, let's say, based on its features, and the root mean squared error is $20, whoa, that could put everything out of whack, right? So what we need to do here then is compare your error metric for the regression task to the average value of the label, which is the average value in your data set, and then you'll be able to try to get an insight into its overall performance. Make sense? And as always, domain knowledge also plays a really important role here. So again, machine learning is not done in a vacuum. It's usually done as a collaborative process. So if you're predicting the prices of a house and you want to get an idea of whether your root mean squared error is good, probably it's a good idea to start talking to someone with experience, like I don't know, real estate agent? Okay, obviously it's just an example, but you get the point. So here we've learned a few different metric sets that you can use to evaluate the performance of a regression task. That's it for this, and I want to see you in the next lesson. Hello, dear friends. Welcome to the machine learning of Python. So now that we've had an introduction to machine learning, in this tutorial, we're going to discuss how to use Python and the scikit-learn package to perform machine learning with Python. Sounds pretty good, huh? So let's get started. Scikit-learn package. Now, that happens to be the most popular machine learning package for Python, and it has a lot of algorithms already built into it. You'll need to install it in your command line or terminal using conda install scikit-learn. Now, if you have an Anaconda distribution or another distribution in Python, you should write !pip install scikit-learn in your command line. Okay, so let's talk about the basic structure of how to use scikit-learn. Well, first, we need to back up a little bit and review the machine learning process. But just briefly, don't worry. So the machine learning process starts with your data. You have to acquire data somehow, and then the next step is usually to clear and format that data. So then the machine learning model can accept this before you give it to the machine learning model, right? And as part of that process, by clearing this data, you will split it into a test set and a training set. Train your model or training set. And then in the next step, test your model in the test set and repeat your model and adjust the parameters of your model until you're ready to deploy. All right, so now let's do an example using scikit-learn. Now, I don't need you to worry about memorizing any of these. You will see these steps over and over and over again, and we'll guide you through each of these steps. So just hang on for the ride. In fact, we're actually coding out the algorithms. So remember, this here we're doing is just an overview, and this will make it very familiar for you when it's time to be coding it out. Okay, so every algorithm in scikit is exposed via an estimator object. You will first import the model, and the general form of this is to say from sklearn.family import model. So as a specific example, it would look like this. Let's say that we want to perform a linear regression, which will be the first machine learning algorithm that we learn. We'll go ahead and say from sklearn.linear_model, where linear_model is the family of models. Import, and then linear regression. And that linear regression is that estimator object, and that's the model itself. And then the next step would be to embody this model or estimator. So all parameters of an estimator can be adjusted when they all have appropriate default values. And then we will explore these values and these parameters using Shift-Tab in Jupyter Notebook. Check all possible parameters. For example, you can start a linear regression model by simply specifying a parameter as normalize equals true, and then after printing the model, you just instantiate it. You can go ahead and check the parameters such as intersection true and copy x equals true, which is the default for the model. I actually don't need to specify normalized as equal to true because these are additional parameters that you can use to tune the model to something more specific. So after your model has created your parameters, it's time to fit your model to some data. But keep in mind that we need to split this data into a training set and a testing set. So I'll make an example here of how we can do just that. So I'm going to go ahead and say import numpy as np in order to create some fake data. And then we can use scikit-learn to do train test split, splitting our data into training set and testing set. And then we're going to say from sklearn.model_selection import train_test_split. Then we're going to have our sets of data, x and y, x being the actual features and y is the actual label for each of those feature rows. And then, using train test split, you will pass in x and y, and you will pass in the test size. Now, again, don't worry too much about memorizing or fully comprehending everything here. We have a lot more practice later on with this process, but I just want to give you an overview so you can use train test split on your features and labels, and scikit-learn will automatically output your training set and your testing set. All right, so we have x-train and y-train, and x-test and y-test. And of course, you can see how these arrays are outputted here. All right, so basically you have attributes for your training and test data, as well as labels for your training and test data. So now that we've split the data, we can train or fit our model on the training data. And this is done through the model.fit method. So basically, you take your model. Now remember how we embodied it as a linear regression estimator. And then you can say model.fit and pass in your training data. And then you pass in your X training data, which are the features of your data. And then you pass in your Y training data, which are the training labels. All right, great. So now you see how the model has been fit and trained on the training data. And this makes the model ready to predict labels or values on the test set. Again, remember I'm showing an example of a supervised learning process. The process for an unsupervised model is going to be a little different because you're actually not going to be having these labels. But every supervised learning model will get the predicted values using the predict method. So we'll just go ahead and say model.predict. Pass in your X test data, and those are your test features, and you get predictions from that. So here's where you can evaluate the model by comparing the predictions with correct values. So the evaluation method depends on what type of machine learning algorithm you are using. Different evaluation methods, of course, are used for regression versus classification versus clustering, and that goes on. But we'll go ahead and we'll just get a quick summary of all this. Scikit-learn, well, really strives to have a uniform interface across all methods, and we're going to see some examples of that below. So given a scikit-learn estimator object named model, these following methods are available. In all estimators, you're going to be able to fit to the training data. Then for supervised learning applications, this will be X and labels Y, except for 2 arguments. For unsupervised learning applications, this only accepts a single argument. The data which makes sense because unsupervised learning works on unlabeled data, right? Okay. Now, Available in supervised estimators, you're going to have a predict method which, given a trained model, is going to predict the label of a new set of data. So this method accepts one argument, the new data, which is going to be x_new. So in this example, or in the previous example, it was x_test. And then this returns the learned label for each object in the array. Great. So also available in supervised estimators is the predict_proba method. And then for classification problems, some estimators provide that method, which returns a probability that a new observation has in each categorical label. So in this case, the label with the highest probability is returned using the model.predict method. For classification or regression problems, you also have a score method available, and in most estimators will implement this method, and scores are between 0 and 1, with a larger score indicating a better fit. Also available in unsupervised estimators is the model.predict. And of course, that will allow us to predict labels in clustering algorithms, and again, that's in unsupervised estimators. But also, when you're given an unsupervised model, you'll also have the model.transform method, where you can transform new data into new bases. Now, we'll, of course, go into much more when we talk about unsupervised learning algorithms later, but basically, this also accepts one argument, x_new, and returns a new representation of the data based on the unsupervised model. And again, I don't want to jump the gun here, but I just want to contrast the differences here. We're going to dig way deeper into that topic, and I'll explain it in a lot more detail when we talk about unsupervised machine learning problems. But there's one more thing here, and I want to point this out, that there is the model.fit_transform for unsupervised estimators. Now, some estimators apply this method, which performs a fit and transformation on the same input data, just more efficiently. All right. So now you might be wondering, well, okay, so how do I choose an algorithm classification versus regression versus clustering? Well, if you go ahead and just write scikit-learn algorithm cheat sheet in your Google search bar or wherever you want, you're going to get a picture like this. And this is from the official scikit-learn documentation. But basically, this is a bit of a decision tree or a guide on how to choose an algorithm. And if we go ahead and start, you'll see that it has asked you more than 50 examples. If not, you really should get more data. So if you don't have more than 50 samples, then it asks you, are you trying to predict the category, predict the quantity, whether the label is data, etc., right? Okay, my dear friends, so we're going to start Python for machine learning by launching our first machine learning algorithm, which will be linear regression. All right, so thank you very much, and I want to see you in the next lesson. Hello, dear friends. In this lesson, we're going to learn supervised learning. All right, let's get started. So the supervised learning algorithms are trained using labeled examples. And this is a keyword label, like an input where the desired output is known. So that means it's in your data set. So you're going to have some historical features with historical labels. So you already have this information. For example, a piece of text might have a category label. So you get a bunch of previous emails, and someone has already gone and classified them using the correct label. And then they read the email, classified it as legitimate, it's not spam, or we have a lot of movie reviews, and someone has already labeled the movie reviews positive or negative for the movie. You get where we're going. But see, then the idea would be that for future text information, such as incoming email using historical label data, the network or machine learning algorithm could learn from historical data to predict whether the new data belongs to spam or legitimate, or positive category, negative category for if we're talking about the movie reviews, right? So the way this works is it networks, neural networks, and takes a set of input data along with the corresponding correct output. And then the algorithm or network will learn by comparing its actual output with the correct output to find errors. And then it'll change the model accordingly, such as adjusting the weights and bias values in the network. So supervised learning is used in applications where historical data predict likely future events. And the machine learning process for supervised learning looks like this. So let's go inside and take this step by step. So the first thing we'll do is actually get the data, and then depending on where that data actually comes from depends on what field you work in. So it may come from your customers, or it could come from collecting things online into a database, or maybe from physical data and sensors, so forth and so on. So in other words, at some point, the data has to be actually acquired. Then once we have actually obtained the data, we need to clean the data, format the data so that our neural network can actually process it. And we usually do this using a library called pandas. And then we split the data into training data and test data. But indeed, what we're doing here is we'll take some of our data, maybe 30% as test data, and then maybe 70% of it will be our training data. And then what we're going to do here is we'll use this particular training set on the neural network or model to fit a model to that training data. And then we're going to want to know how well our model actually performed. So we run this test data across the model and compare the model's prediction with the actual correct label, which is the next test data. Because remember, we know the correct label for this test data here. Yeah? So then you can run these test data features through the model and get our model predictions and compare with the correct answers. And then, of course, we can evaluate the model. And then maybe you want to go back and look at the performance and adjust the model parameters. You might be able to add some more layers or maybe some more neurons, right, to try to better fit that test data. So once you're satisfied, you can then deploy the model to the real world. I got to remember here, one thing to note is that we have just showed you a very simplified approach to technically supervised learning. And this includes an important issue that we touched on during the test-train split. And this is the question that arises. Is it okay to use a single data split as a single test set and a training set to truly evaluate the performance of your model? You follow? So naturally, when you actually test your model on the test data, you'll get some kind of performance metrics for regression task. And it should be something like a root mean squared error. For a classification task, it could be something like accuracy. But is it actually fair to use accuracy that you get from the test data as the final performance metric of your model? After all, technically, you were given the chance to update the model parameters over and over again after evaluating your results in that test data set. So how can we evaluate this concern? Is there anything to correct? I would say yes. So in order to fix this problem, data specifically in neural networks and deep learning are actually divided into three groups. And we have training data, validation data, and then test data. So we kind of introduce this in between step of this validation, right? So what we wind up doing here is we've got these three sets, and we have the training data, just like we did before. And then this is used to train the model parameters. So the model looks at the features, looks at the correct output, and then fits that training data. And then, of course, the next step is our validation data, which is our previous test data. And so what we do with this validation data is after training on the training data, we check the performance on the validation data. And maybe we go back and adjust our models based on this performance. And then maybe adding more neurons or adding more layers. Well, that'll change the actual architecture of the network. And then you repeat this process over and over until you're satisfied with your model's performance in validation data. Okay, my dear friends, now we've got that. It comes time to evaluate the true performance of your model. So, what do we do? Well, see, that's why we created that third split of test data that the model has never seen before. And what you use is this final test data set and actually get some final performance metric. Now, the most important point to note here is that when you run the model on the test data, your model will actually be the performance metric you expect it to perform in the real world. So when you actually get into that final test data set, as you won't be able to go back and adjust your models, weights, or parameters, or anything else, you are technically not allowed to go back and adjust the model to try to improve your performance in that final test data set, right? Right. So you can think of it this way. You train the training data to really fit your model. You then use the validation data to see how your model is performing and data that is not visible. And then go back and adjust your hyperparameters. However, when it comes time to let your boss actually know how successful this model will be in the real world, well, that's where your final test data set comes in. And the test data set. Once you've actually gone through the test data and got this performance metric, you can't really go back and adjust hyperparameters. Otherwise, you're going to fool yourself again and understand the actual performance of models on data that is not really visible. So this means that after seeing that result in the final set of tests, we can't go back and adjust any of these model parameters. This final measure is what we label the actual performance of the model on visible data. Okay, dear friends, so in this lesson, we're going to simplify our data by just doing that single train test split. Now, technically, while we could be doing another split to get both validation and a test set for the kind of problems and exercises that we're doing in this course, since we're not really deploying a lot of these models into the real world, it's not going to be such a huge deal that we essentially just have a training set and a test set, and we just give the sort of, validation in between set. So just remember what we're doing and what the process is. So what we're doing here for this course is we're simply going to train and then evaluate on a test set and go back and leave the option to set up the hyperparameters to you, all right? And then after completing the entire course, you're going to be able to easily perform another split to get those 3 data sets because you desire perfection. All right, well, maybe not perfection, but okay. Anyway, you'll be able to easily create a training set, a test set, and a validation set, if that's what you want. But I just want to tell you that in this course, we're going to keep things simple. Just train on a training set and then evaluate on a test set. And that way, we're really not going to go back to adjust hyperparameters. We're just going to treat that as the kind of final test set, right? But again, you can always go back, add more neurons, add more layers, add more hyperparameters to your network. It's going to be up to you because it's really easy to do and it is a must do. We'll kind of leave that up to you, though, as you continue to learn, because you really should want to continue with that. All right, my friends, so to recap all of this, we have really dug into supervised learning. And I hope you're inspired by this. I want to see you in the next lesson. Until then, have a really nice day. Hello, dear friends, and welcome to the introduction to linear regression. So in this lesson, we're going to get a light theoretical background, perhaps, we'll say. Anyway, we're going to get behind the idea of linear regression before we actually tackle the concept with Python and the scikit-learning library, okay? So now let's get into that background. Linear regression. So the entire idea all started way back in the 1800s, believe it or not. There was a man called Francis Galton, and Galton was working on relationships between parents and their children. Especially, he was exploring the relationship between the height of the fathers and their sons. What he discovered was that a man's son tended to be roughly as tall as his father. However, Galton's breakthrough was at his son's pinnacle, tending to be closer to the overall average height of all people. So let me show you, and I'll just make an example of this. Okay, so LeBron James, very tall. Well, of course you have to be as famous as he is for playing in the NBA. Anyway, without getting into any controversial figures, let's say, just for the sake of argument and mathematics, that he is 6 feet 7.5 inches, or 2.06 meters tall. Now, if LeBron has a son, as it's known, he will also be quite tall. But LeBron is so abnormal in his height that it is very likely that his son is not going to be as tall as LeBron. And it turns out that this is the case. So LeBron James' son is quite tall. He's 5 feet 8 inches. Not quite as tall as his dad, though, who is 6 feet 7.5 inches. Now, Galton called this phenomenon regression. Okay, you with me? Just like a father's son's heights tend to regress or slide to the mean or average height of everyone else. Okay, so let's go ahead and begin to plot out the example so that you can see. We'll calculate a regression with just 2 data points, which is the simplest possible example, right? So here we have 2 data points, x equals 2, y equals 4. And so this is one data point. X equals 5, y equals 10. This is our other data point. These 2 little black dots. Now the only thing we're going to try to do in calculating our regression line is to draw a line as close to each point as possible for the classical linear regression, or least squares method. So you measure proximity only in its up and down movement. Now we have a perfect line here because we only had 2 points. But wouldn't it be great if we could apply the same concept to the graph with just more than 2 data points? So by doing this, we can take the height of multiple men and their sons, and then perhaps predict for a guy how tall his son is going to be, even long before he has one, right? So this is the idea behind supervised learning. We're going to have a bunch of labeled data points create a model. So in this case, we're going to use regression theory and try to take unlabeled data, such as a father's height, and then spit back out some labeled data. So we'll have a group of labeled data points forming a pattern. And in this case, we'll theoretically try to retrieve unlabeled data, such as regression and father's head, and return the labeled data to our estimate of his son's height. Now, with linear regression, our goal is to minimize the vertical distance between all data points and our line. Therefore, when we determine the best line, we try to minimize the distance between all points and their distance from our line. There are actually many different ways to minimize this, some of errors, some of absolute errors, and so forth and so on. However, the general purpose of all of these methods is to minimize the distance between your line and the remaining data points. Yes? For example, one of the most popular methods we have that I just described is the least squares method. Here are a few blue data points along the x and y axis. So now we want to fit a linear regression line. So the question then becomes, how do we decide which line is the best fitting one? Well, we can go ahead and use the least squares method that we discussed. This method is fit by minimizing the sum of the squares of the residuals. The residuals for an observation is a difference between the observation of the y value and the fitted line. Follow? So in this image, the residuals are marked by the red line, the difference between true data point in blue and your fitted model line, black baseline. All right, my dear friends, to recap, we have just learned a theory part of our linear regression. So I want to see you in the next lesson, and we'll have some fun with that. Well, hello, dear friends, and welcome to Fun with Linear Regression. Just playing, but no, it will be fun. Anyway, linear regression with Python, okay? So we've already learned the theory behind linear regression. So let's go ahead and use scikit-learn so that we can implement our own linear regression models. So we'll start by working with a housing data set, and this tries to build a model for predicting house prices based on available properties. So as linear regression is our first machine learning algorithm, we're going to be working with some artificially generated data sets. So we'll continue to use real and more complex data sets later, but you don't want to focus too much on the cleanliness or the data right now. We're just going to focus on the process, and we'll get true later, all right? So right now, we just want to get the basis of how we create this model. Okay, so let's go ahead and jump into the notebook and get started. All right, now before starting up the notebook, a little public service announcement here. With this notebook, the CSV file that we're going to work on must be located in the same directory. You remember this, right? Otherwise, you will get an error while you're importing data. All right, so double check that. Let's go ahead and get started. First thing is we have to import, and what's going to happen here is we're going to say import pandas as PD, and we're going to say import numpy as NP. And then we're going to need to import our visualization libraries. I'm going to say import matplotlib.pyplot as PLT and import seaborn as SNS. And then in order to see these visualizations in the notebook, I'll need to specify %sign matplotlib inline. Okay, so let's go ahead and take a look at our data. So I'm going to create a data frame named df and say pd.read_CSV and call predict_house_price. And let's go ahead and check the head of the data frame. We have a total of 7 columns in this data frame. We have rows representing a particular house in here. The last row is the price column, and the house is sold at a specific price. Good, so these other columns represent statistics for the city or region where the home is located, such as, let's see what we've got, the city's population, the average number of bedrooms for houses in that area, number of rooms on average for other houses in that area, average house age for houses, and people's average income. Okay, so these are all good. But again, these first few rows that start with the mean area correspond to the location or the city of that house. And remember, of course, this data is just, for example, it's artificially created, so any significant numbers after the decimal point, they're usually going to have that much accuracy. Okay, so dear friends, now we can go ahead and examine this data a little bit. So what I always recommend you do is take a good look at the info method. And this is right here on your data frame. And this will give you information about the total number of columns and the total number of entries. Now, besides giving a few clues or statements about what types of objects there are in the data frame, the other thing that I would also recommend you do is call the describe method, and it gives you the ability to get a quick account. So this method gives us statistical information, such as the mean, minimum, and maximum value, standard deviation, etc., the numerical columns. So notice here the address column, well, it's not available because that was a string value. Another quick note here, if you ever need to reference the column names, well, you can just say df.columns and return back a list of the column names. So let's go ahead and do some simple plots to examine our data. One very simple plot you can do if the data isn't very large is Seaborn pair plots. And then you can just pass the entire data frame. And this will automatically generate not only histograms of all the columns, but also correlate scatter plots. And this is what that looks like. You can see the histograms that everything seems to be more or less normally distributed except for the average number of bedrooms column. And you'll notice that the average number of bedrooms is divided into 2, 3, 4, 5, and 6. And there's some noise around here, but usually can't have 2.5 bedrooms, so that's why this kind of behavior occurs. Okay, so let's go ahead and look at the distribution of one of the columns. Now, you'll most likely want to check the distribution of your target column, or what you're trying to predict. So in this case, we're trying to predict the price of the house. So let's go ahead and check out the distribution of the price. Okay, the average price seems to fall somewhere between 1 and 1.5 million, around 1 million, and everything seems to be distributed from there pretty normally. Now, of course, this won't always be the case when it comes to pricing or other target variables. They might not be distributed normally, but that's a nice case because we're not really trying to clear this data, okay? Oh, and the other thing that you might want to do for a data set is to make a heat map of the correlation between each of the columns. So you can say df.corr, and this will give you a correlation matrix. So let me just go in here and show you what that looks like. df.corr, and this is the correlation between all the columns. And then you can plot that out as a heat map just by passing that in through the SNS.heatmap. And then here we can see that in general, you'll see the diagonal of the exact correlation, and that's meaningful because each column itself has to be perfectly correlated, and then you will also be able to see some information based on other columns. So right now we get a lot of gray and low correlation amounts, and you can actually see this numerically just by saying annote equals true. All right, so let's go ahead now and shift our focus to actually using the scikit-learn and training a linear regression model. The first thing you're going to want to do is split the data into an X array with the properties to train, a Y array with a target variable. And in this case, the price column we are trying to predict will continue, and the address column will be thrown out because right now it only has text information that the linear regression model won't be able to use. Okay, so I'm going to go ahead and say df.columns to grab my column names, and then I will set x equal to df, and then pass in a list of the column names, and I can just go ahead and actually grab this from here and paste it. Or I'm going to say x equal df.drop, and then write the columns that we want to drop in brackets. So the address variable that we will not use in our price and model, which is our main target variable, we have to set the axis parameter to 1 because we want our columns to drop. And then y is going to meet my target variable. So what I'm trying to predict in this case is the price column. Right, so now that we have x and y data, our next step is to do a train test split. So we want to split our data into a training set for the model and then a testing set as well so that we can test our model once it has been trained. So we're going to go ahead and use scikit-learn to do this. So scikit-learn comes with a train test split function, and you can just grab it by saying from sklearn .model_selection, and then you want to do import train test split. So it's a Shift Tab in Jupyter Notebook to read the documentation string for it. So you can scroll down and see a good example here where you say x train, x test, y train, y test is equal to train test split, x, y, test size, and then a random state that we can add. All right, so we'll go ahead and copy this line, copy it, and I'm just going to paste it here and put it all in one line. All right, my dear friends, let's go ahead and set our test size 0.4 and our random state 101. All right, so let me try to explain what happened here. This is actually using tuple and packaging to get your training set and your testing set. And you're going to have your X train and your Y train. And then you're going to have your X test and your Y test, right? Okay, so then in the train test split function, you can pass in your X data, your Y data, and you optionally choose a test size as well. And this test size, well, it's only a percentage of your data set that you want allocated to the test size, right? Okay. So in this case, we are going to go and allocate 40% for test size. It's also very common to make it 30 or 0.3% most of the time. So then this random underscore state equals 101. You can pass in an optional number here if you want, but essentially it guarantees that a certain number of random splits will occur in your data. Since this train test split will happen randomly, to make sure that your random split is the same as my random split, just go ahead and specify random underscore state as equal to 101. That way we'll get the same random splits. Right? You follow, right? Otherwise your results might not match exactly mine and somebody's going to be wondering what's what. Anyway, it will still be true, you just won't have the exact same numbers as your result. Okay, so now that we have our training and testing data, let's go ahead and run this. So we have to build and train the model, yeah? So the next step is, say from sklearn dots, and linear regression is found under the linear underscore model family. So we say linear, and you can use the tab to complete this import automatically. And we want the linear regression model. Okay, so once it's imported, the linear regression model will go ahead with this, instantiate it, and here we have an instance of linear regression model. So I'm going to go ahead and make a variable called lm equals, and then say linear regression, and instantiate some basically creating a linear regression object. Now I'm just going to say lm dots, click tab, and we'll check out all the available methods. If there are all these available methods in my model, then the first thing I'm going to want to do is use the appropriate ones to train or fit my model or training data. So I'm going to choose fit method. So if we look at the shift tab, Well, this method will take an X and Y and so on and fits the linear model. So in this case, I just want to fit my model to my training data. So instead of just passing in X and Y, what I'm going to do is say X train, Y train. And I know that I get an output telling me the linear regression model was trained. Now notice also that I didn't set this equal to any other variable object. This already has an effect on the object itself. So I don't mean to say lm equals lm.fit. You can just say lm.fit. Okay, so now the next step is to evaluate our model by looking at its coefficients and then seeing how we can interpret them. And let's go ahead and print the intercepts. I can grab the intercept by calling for my model, lm, and then saying intercept, and then underscore at the end. Or you can just use tab autocomplete. All right, so the next thing you can check are the coefficients, and the coefficients will be related to each feature in our data set. You can grab the coefficients by saying lm.coef underscore, and this will return the coefficients for each feature. Okay. Now, to organize this a little better, let's go ahead and create a data frame based on these coefficients. So each of these coefficients relates to the columns in X or X train. So just go out and check that these are the same columns, X and X train. So what I'm going to do is to go in here and create a data frame off of these. So I'm going to say PD data frame, pass in the coefficients as my data, pass in the columns as my index. And I'm going to go in and say columns is equal to coef. All right, so let's go ahead and set this equal to CDF for coefficient data frame. And then we'll call the CDF now. All right, so here we have a coefficient for each feature. And perhaps if you want a more mathematical reasoning behind these coefficients, just ask to read how they work. And I'll briefly explain how to interpret these coefficients. Basically, what does this mean? Well, if we look at the former, keeping all the other features constant, a 1-unit increase in average area income is associated with an increase in price of $21.52. And then for the latter, we could say something like an increase in mean area house age of 1 unit is associated with an increase of $164,883. And you'll be able to do a similar analysis for each of these features and their coefficients. Now, you might be wondering if this really makes sense. Probably not, because this is indeed artificially generated data. But if you do want to do a real data analysis, you can actually repeat this project on the Boston data set. So this is the same dwelling type data. It, however, happens to be actually true. You can actually find it from research done in the 1970s, and it is in this scikit-learn. But let me just go ahead and show you how to grab the Boston data set. So what you can do is call from sklearn.dataset, import load underscore Boston. Now there's a link in your notebook for the documentation on this data frame. But basically what you do is say Boston is equal to load underscore Boston. And then you call it, you actually call that function load Boston. And then if you check it out, what Boston is essentially a dictionary with a whole lot of information in it. You can check out the description of the data set by saying Boston, DECR. And this will print out the Boston houses price data set. So this is real, actual housing data. So if you want to do a similar analysis for house price data in a real data set, you can repeat the analysis of the lesson here that we're doing. Because if you look at it, this data is fairly old. And then if you want to capture the data itself, you can just say the data, and here you see your data. And then you can also take feature names here, which are essentially columns or data frames, and then capture the target as well. And these are all the target prices in thousands. All right, my friends, you see what we're looking at. So let me ask you that if these coefficients were negative, would you say that for every increase in the unit, you would get a downsize of the price of the house? Well, we'll finish the first part of our analysis here. And then in the second part, we'll discuss getting predictions from our model. But before we get to that second part, let's just step back for a second, take a quick look at everything that we did. So first, we had to actually grab that data using pandas and the pd.read CSV. We did some exploratory data analysis to get familiar, but didn't want to focus too much on that as it's synthetic data. Then we separated our data into X and Y, where X is features, Y is what we're trying to predict. We said from scikit-learn.model_selection, import train test split. We went ahead and split our data by specifying a test size and also specifying a random state. And your results were the same as shown in this video, yes? So then we said from sklearn.linear_model, import the actual model linear regression. And we created a linear regression object, basically an instantiation of a linear regression model. Then we fit this model to the training set and explored the intercept and the coefficient. Now, if you do want a bigger breakdown of how to interpret these coefficients, you can always refer to the Jupyter notebook for this lesson. And then we simply formatted the coefficients into a nice data frame so that we can read it by a human. All right, and then at the end, we showed you how you can access a real data set from scikit-learn. To grab this data set, we said from sklearn.datasets, import load Boston. And in case you want to repeat the sort of analysis on a real data set, you can use this. All right, so that gets us up to here, but we're not quite finished yet. So in part 2, we'll discuss how we actually grab predictions from our model based off of that test set. All right, thanks very much for sticking to it and getting this far. I look forward to seeing you in the next lesson. Hello, dear friends. Welcome back. So this is the beginning of the second part of the linear regression lesson of using Python. So we're going to focus now on getting predictions from our model. So we'll go ahead and go back to the notebook that we started last time. And here I am in Jupyter Notebook. You might recognize it. And we're able to create our latest model and fit the model to our training set. So now we want to grab predictions from our test set. So what you can do is say predictions is equal to lm dot. And then we're going to call the predict method. In the predict method, use pass in the X, just the features. So in this case, we want to pass in features that the models haven't seen before. So we want to pass in X_test, which is the testing set, and just the features. Then we can go ahead and then check the predictions. And if we just look at the array of predictions, here's a ... These are the estimated prices for the house. However, since we did train test split, we know that the Y test includes the correct prices for the house. And we want to know how far the predictions are from the test prices to real prices, right? So there is a quick way to analyze this visually just by simply making a scatter plot. So you can say something like plt.scatter from matplotlib and compare Y test with your estimates. And if they line up something like this, you know, you're doing a pretty good job. So this means that a perfectly straight line will be completely accurate in its predictions, right? So getting a little out of the straight line is actually a very good job. So let's go ahead and actually create a histogram of the distribution of our residuals. So I'm going to say SNSDistPlot. And with the residuals, remember these are going to be the difference between the values predicted by the Y test. So I'm just going to go ahead and pass in Y test minus predictions. And we can go ahead and create a plot like this. So now this is going to be a histogram of the residuals, right? So notice that our remains here appear to be scattered normally, which is a very good sign. If you distributed the remains normally, it means that your model is the right choice for the data. So of course, the converse is true if this is not normally distributed and you have some sort of a, weird behavior going on here. You might want to go back to your data and check to see if a linear regression model is the right choice for your data set. There are others. So later on in the machine learning section, we'll discuss a few of those other ways to analyze your model choice. So now let's go ahead and continue with regression evaluation metrics. There are 3 general evaluation metrics for regression problems. I'm going to quickly jump back to Jupyter Notebook containing the notes for this lesson to explain these assessment criteria. Okay, so I'll go ahead and jump to Python Notebook's Linear Regression. And as I mentioned here, there are 3 regression evaluation metrics, right? At least 3 of the most common. There's the mean absolute error, which is the mean of the absolute value of the errors. There's the mean squared error, MSE, which is the mean of the square 2 errors. And then there's the root mean squared error, RMSE, which is the square root of the mean of the squared errors. So these are all fundamental variations of the difference between what you predict and actual values. So now we can go ahead and compare these metrics. The mean absolute error, MAE, is probably the easiest to understand because it's just an average error. You take your error and get its absolute value and average. Mean square error, MSE, is a bit more popular than mean absolute error because MSE penalizes larger errors, meaning it tends to be more useful in the real world because it takes into account larger errors because it's going to square them. RMSE is even more popular than MSE because RMSE can be interpreted in Y units, meaning you can directly interpret RMSE in Y units regardless of your goal. And then these are all lost functions because, we want to minimize them. So all these values here are something that we want to minimize. We want to minimize all these errors so that we can create the best model. Make sense? So let's go ahead and go back to finish calculating out these metrics in our notebook. All right, so back in the notebook, we can calculate all of these just by saying from scikit-learn import metrics. And you can say metrics dot mean underscore absolute underscore error. And this will take in your Y true and Y predictions. So in this case, that's Y tests in our predictions. And you can go ahead and print it out. In this case, it is your mean absolute error. Now, similarly, you can go ahead and calculate the same thing for your mean square error. And I'm just using tab to autocomplete it here for Y test and predictions. Great. So the other thing I could also do is grab the root mean squared error. And you could easily do that just by using one of NumPy's universal functions, np.sqrt. And then move on to our previous result here. Since that was the mean squared error, it works. So if you want the root mean squared error, we just pass that in. And that gets us the root mean squared error. So what do you say, my friends? That leads us to the conclusion of the explanation of linear regression model. So to recap, we've successfully taken the data according to the futures and target, split the data into a training set and a test set. So please go ahead and come back here to train a linear model. Fit the model, check the coefficients and intercepts to learn a little bit about the model, and then make predictions using the model and analyze our residuals. So basically, it's our model error based on the test set, and we can actually check the metrics themselves. Okay, so as I mentioned, if you want to redo this analysis in a real data set, you can. Just go ahead and explore the Boston data set that I mentioned earlier, and I linked to your notebook, actually. All right, my dear friend, so the next step, we're going to give you some e-commerce data, and you'll then need to create a linear regression model by following the instructions in the exercise. And then we'll go over the solutions. So I hope you enjoy linear regression, the first entry model in machine learning. All right, thanks very much, and I'll see you in the next lesson. Hello, everyone, and welcome to the Linear Regression Project Exercise Overview. So in this lesson, we're going to get a brief overview and background for the project exercise notebook related to the Linear Regression project. If you're ready, let's go ahead and jump into the notebook right now. All right, so you can see that I'm here in the notebook, and as a quick note, you can find this Linear Regression project exercise book under the Machine Learning Linear Regression folder. Now, you'll first notice that there are two notebooks here, Linear Regression Project and Linear Regression Project Solutions. I know some people just want to jump to the solutions, but it's all about the process. Anyway, just go ahead and try to practice before examining the solutions. You get it, right? So this is where all the code will be filled. Then you will see an e-commerce client file as well. And that's just going to be the source of our data for this project exercise. Okay, so let me go ahead and I'll give you some background for the project. All right, so picture, if you will, you've contracted with an e-commerce company based in the United States and selling online clothing, but the store also has in-store style and clothing advice sessions. So customers can go into the store, hold sessions or meetings with a personal stylist, and then go home and order their desired outfits via the mobile app or website. So the company is trying to decide whether to focus its efforts on mobile app experiences or website experiences. And they've hired you under contract to help them understand. And then you can go ahead and get started just by analyzing customer data. Oh, and another short note, we are going to be dealing with some artificially generated data. There are credit card numbers and emails, but don't worry about none of that. So in other words, it's not real, okay? So they are data, that's what's important. And go ahead, import the data, and then follow the instructions that are in bold. And if you don't want to overwrite the existing output, then you should probably keep in mind you might want to add cells. All right, next you'll do some exploratory data analysis with Seaborn by creating some of these visualizations and diagrams that attempt to understand the data. And you'll understand some questions about the data. You'll then create training and test sets for your data, train a model, and predict based on your test data. You'll then evaluate your model and also look at the residuals, and you'll be able to come up with the results. Okay, my friends, good luck to everyone in the project exercise. Thank you, and I certainly hope you enjoy the project. Good luck. Hello to everyone, and welcome to the Linear Regression Project Exercise Solutions lesson. So in this lesson, we'll begin to examine the solutions of the Linear Regression Project. All right, so right here, I am in Notebook, as you can see. So why don't we just go ahead and get started. First thing we will need to do is all of our imports. And so I'm going to just go in and import pandas and numpy. And I will also import my visualization libraries, matplotlib.pyplot as plt, and Seaborn as SNS. I also need to specify %sign matplotlib inline. And we will continue with the instructions and say import scikit-learn as we need it. All right, so then we want to get the data from the company as we will be working with the e-commerce client CSV file. All right, so it's got 4 columns. We'll go ahead and read it as a data frame called clients or customers. And we're going to say pd.read_CSV. And then we can start writing whatever we want. And if we just click on the tab, it will be auto-completed for us. Great. So let's go ahead and say customers.head. And that way we'll get to look at the top of the data frame. And of course, well, it's a hope of mine, I guess, that you're used to this kind of interaction with the data set by now. So we notice here that we have our email address, our membership image, and we have numerical columns such as mean session length, time spent on the app, time spent on the website link for membership, and annual amount spent. We can also scroll to the right to see them. We can also examine the describe method. That way we can get some statistical information about the numerical columns. And we can use the info method to get some basic information, such as object types, how many entries there are, how many columns there are. All right, so it looks like we have 500 rows, 8 columns. Now let's go ahead and start doing some exploratory data analysis. And remember that for the remainder of the exercise, we're only going to use the numerical data of the CSV file. So the first thing that you want to do is use Seaborn to create a joint plan to compare the time spent on the website columns and the annual amount spent columns. And this is then going to be the correlation shown that makes sense. So let's go ahead and do this. Now, if you haven't achieved the exact color, the plot should look like this story. All we can say is sns.jointplot, and we'd like to compare the time spent on the website with the annual spending amounts. So we'll go and determine that our data will be the customer data frame, and then X is going to be time spent on the website. And that makes Y free to be annual amount spent. Cool, so there it is. Now, when trying to interpret the type of scatter plot, well, there doesn't seem to be a clear trend between the time spent on a website and the annual amount spent, just by looking at it visually. So, okay, then we'll just go ahead and take a look at this later when we actually start building our model. Right now, we're going to move on and we'll do the same, but with the time spent on app column instead. So as I show you here, the time spent in app, X, and the annual amount spent, Y. Now here we should see a slightly greater relationship between time spent in app and annual amount spent. So we'll do this by saying sns.jointplot. And again, you say your data is equal to the customer. And the order of these arguments doesn't really matter as long as you specify which parameters or arguments are actually passed. So I want to say time spent on app and annual amount spent. Now remember, the specification capitalization must be exactly the same as the column name. Do you remember that too? Of course. So for instance, customer wasn't correct. So I'll need to say data equals customers. Okay, and here we have the same plot. And there's going to be some sort of relationship between increasing the time spent on app and increasing the annual amount spent. So we'll go ahead and use the joint plot to create a hex plot. And that'll compare time spent on app with the length of membership. And we can do this again with joint plot specify. X is equal to time spent app. Y is equal to length of membership columns. And then we'll specify kind as equal to hex in order to create the hex bin plot. And finally, we want to say data is equal to customers. So let's run that. And now we see the hex plot. Very cool. So let's go ahead and examine such relationships across the entire data set using the pair plot to recreate the plot below. And don't worry if you can't get those same colors. You can just say SNS point pair plot and then pass in your customer's data frame and run it. Now, because it is a larger data set, it may take some time depending on your computer. Okay, so you should get something that looks like this. Now, based on this plot, it seems to be the most relevant feature of the annual amount spent. So, depending on whether you go ahead and look at the X or Y axis, we can look at the column annual amount spent, which is right here at the bottom. So annual amount spent, we're just looking at this visually. It looks like it could be the highest correlation right here. Seems more like a straight line. And this is the length of membership. So then the answer to this question, visually based, is the length of membership. So what we want to do now is to create a linear model plot using the Seaborn LM plot of annual amount spent versus length of membership to try to draw this relationship a little bit more clearly with some detail. And we can go ahead and say sns.lmplot, where we want X to be the length of membership, Y is equal to annual amount spent, and data is equal to customers. And then we're going to go ahead and run this, and yeah, we've got the same plot. Now, let's notice here that there seems to be a good linear fit to this data. You may also notice this because as long as these error bars go away, there are very few errors. So we know a pretty good idea that the longer you stay a member, the higher annual spending you're going to make, which again makes sense. So now let's go ahead and generate our training and testing data. And we'll start this by specifying a variable X equal to the numerical properties of customers and a variable Y equal to the annual amount spent column. So let's take a look at our column names, saying customers.columns. And this will make it easier than writing down a lot of information, right? So I can go ahead and say Y is customers, and what we're trying to estimate is the annual amount spent. And then for X, what we want are data frames numerical columns. And that's going to be equal to mean session length, the time spent on the app, time spent on the website, length of the membership. So let's go ahead and put that in. So customers, and then take in a list of the column names, and then go ahead and put this on one line. But that should give us numerical columns. Okay, great. So we have Y data, we have X data. Y is what we're trying to predict, and X are numerical properties for it. So we'll go ahead and then use the model selection train test split from scikit-learn, and that'll split the data into a training and test set. And we will set the test size equal to 0.3 and the random state to 101. Okay, so you'll always do this in the machine learning section, right? So you'll pretty much memorize this eventually. But we'll say from scikit-learn model underscore selection, and you can tab to get these options, then import train test split. And then we can go ahead and say, well, I would like to do train test split, do shift tab, and see the full documentation string. So scroll down until you come to the examples, and you'll see an example here, and go ahead and just copy and paste it. And then this kind of thing saves you a lot of typing, of course. And now you want to do a set, the size to 0.3 and random state to 101. Now you don't need to set the random set to 101, but if you want your results to match mine and your solutions notebook, you should set the random state. Otherwise, under normal circumstances, you can just leave default random state and you don't have to add this parameter. Cool. So let's go ahead and run it. I'll make sure that everything works out correctly. Okay, so now it's time to train our model with our training data. We're going to go ahead and import linear regression from scikit-learn.linear model. So what we want to say is from scikit-learn.linear model, and you can do tab autocomplete, import linear regression. Then we're going to create an example of a linear regression model called LM. So let's go ahead and create that object. And then LM, we want to fit all training data. And we'll do this by saying lm.fit. So here, if you do shift tab, it will tell you in what order you want X and then Y. And since we are only dealing with the training data, we'll say X train, Y train. And go ahead and fit that. All right, so now we have our fitted trained linear regression model. We're going to print out the coefficients of the model, and we can do that just by saying lm dot and start typing coefficients. And eventually at coef underscore, this will return the coefficients as an array. Well, let's keep guessing from our test data, shall we? Now that we have a fit model, what we can do is predict the test values and evaluate its performance. So we had to use lm.predict to predict the X test set, and we can pass in the X underscore test, then match the results to a sequence called predictions. And then we want to create a scatter plot of actual test values versus predicted values. So we can go ahead and say plt.scatter, pass in y-test, and then pass in predictions. And we can say plt dot, we'll go ahead and do some labels here. We'll say X label number is our y-test. It is true values. And plt.ylabel is the predicted values. And if we go ahead and run this, notice that our model is actually in pretty good condition. Now, this would mean if all points on top of each other had an absolutely perfectly straight line, we have a perfect pattern in test data. But for now, we can see a bit of error, but looking at the predicted values versus the y-test, and the fact that we only use it for numeric columns, yes, this is pretty good. Okay, so let's go ahead and actually evaluate this model, not just visually, but with a little bit of math. So now let's evaluate our model performance by calculating the sum of squares and explain the variance score, which is r squared. Now, do you remember from the previous lesson, we can do all of this just by saying from scikit-learn import metrics. So we can start by saying print MAE, or they are mean absolute error. Okay, so I'm going to go ahead and then call metrics.mean, in this case, mean absolute error. And we just pass in the y-test, the true values versus the production values. So let's just go ahead and copy and paste this answer. You're actually going to be using this answer quite a bit. So the same cell, I can say print MSE metrics dot, and in this case we want mean squared error. And I was going to copy and paste y-test predictions. And then we want RMSE. So we say metrics dot. Now in this case, we want the mean squared error. And again, copy and paste. But remember, since this is the root mean squared error, we're going to go ahead and say np.sqrt and take the square root of that. Score. And then make sure this runs correctly. We got great and matching results. So now you'll notice that there is another minor issue here explained in the variance score. Now, it wasn't specifically mentioned in the bold instructions, but it was a bonus, okay, if you discovered it yourself. But what you can do is say metrics dot. And if you start typing EX and do tab autocomplete, you will also explain the variance score. And this is the r squared value for a regression fit. And you can pass in again y-test and their predictions and see how it ran. So let's go out and check it out. We get 0.98. So if you're not familiar with our square, this is basically a measure of how much variance your model explains. And we explain 99% of the variance. You can see that we've got a very good fit model, especially in the test data. So now let's discuss residuals. So we should have gotten a very good model and a very good fit, just like we saw. So we're going to quickly explore the residuals here to make sure that everything was okay with our data. We're going to draw a histogram of the residuals and make sure that it looks normally distributed. And you can use the plt.hist or seaborn dist plot. So we can go in and just do seaborn and say SNS point dist plot. And we want to say y-test minus the predictions. And we'll go in and specify the bins will be slightly larger, and we'll get a distribution. So it looks pretty normal. And by looking at it, what we're working on, and we already know that we already have a good fitting model, so we shouldn't really worry about the residuals. And then as a result, we still want to find the answer to the original question, which was that we focus our efforts more on mobile app or website development. Or maybe it doesn't really matter to membership. Time really matters. And we're going to see if we can interpret the coefficients at all, in fact, to get an idea. So why don't we do this? Why don't we try to recreate this state of frame below? Now we did this similar data frame, and it's going to do that. So we pass in the coefficients as our data, and we say x dot columns. As the names, we'll call this CDF. We say columns is equal to coef. Now let's go back and check the CDF, and we get the same data frame. Okay, so now the question is, how do we interpret these coefficients? And there is a small reduction cell in case you want to write it here, but you don't have to think about it in your mind. Basically, the way to interpret them is the coefficients one by one. For instance, the mean session length. If you keep all of the properties constant, 1 unit increase in mean session length is associated with about $26 more in spending, right? And similarly, 1 unit increase in time spent in-app is associated with an increase of $38 spent per year. And the time spent on a website is actually shown as a 19-cent increase, which isn't that great. And the membership duration is the strongest feature here, so if you keep all the other features constant, a 1-year increase in membership duration is associated with an increase of about $61. So now the question is, should you focus on the company's mobile apps or, given that information, the website? Now, I'll give you a hint here. This is actually kind of deceptive because there are two ways to think about it. So if you look at our coefficients and the data in our model, we can develop the website to capture the mobile app. Therefore, one way to think about it is that the website needs the most work, and we should concentrate most of our efforts here. Or you could think of it the other way. That is, you have to develop the app further because this already works much better. Understand? So this sort of answer really depends on a number of different factors going on at this particular company or wherever the state is actually coming from. And you're going to want to explore the length of relationship between length of membership and app on the website before you come to a conclusion. And indeed, this is where the role of data scientists begins to blend in with the role of someone with a bit more business acumen and more familiarity with management. So how much will it cost to develop the app compared to the website? And then, that kind of decision tree. So in other words, all of these choices are going to have costs associated with them. And I would say that it's a little difficult to say this without expert knowledge. So what you can do is report and show this information in an informative way, but you will actually need more information about the cost of decisions to choose the right focus. But at least we now have a fully informed history in order to make this decision. You follow? Cool. So my dear friends, I hope you enjoy this project exercise. If you need any reviews, you could, of course, browse through the solution notebook or review the lesson again. And again, the data is not real. It is indeed artificially created. So we will now begin to focus on real data sets rather than real-world problems as we move forward in the machine learning section. So thank you very much to everyone involved, and I want to see you in the next lesson. Hello, dear friends, and welcome to the bias-variance trade-off lesson. It's the one you've been looking for, even if you didn't know that. So in this lesson, we're going to learn about bias-variance trade-off and how you can use them to discuss your model. So bias-variance trade-off, it's basically fundamentally important of how you're going to understand your model's performance and its evaluation. See, the variance trade-off is the point where we are just adding noise by adding model complexity or flexibility. The training error decreases as it should. Test error starts to go up. So the model after the bias trade-off begins to overfit. So let's go ahead and get into this, and we'll imagine a dartboard. So picture, if you will, that the center of this target, or a dartboard, is a model that perfectly predicts the correct values. And the farther from the target, the worse our predictions will get. We'll go ahead and make a low variance versus a high variance quadrant, and high bias against low bias. And this is a good way to visualize and then understand what bias and variance terms actually means. So imagine if we could repeat our entire model building process to get a series of separate hits on the target. Given the variability of luck in the training data that we collect, each of our fit models represents an individual realization. So sometimes we could get good distribution of training data, so we predict very well and we get close to the target. Sometimes our training data can be full of outliers or non-standard values, resulting in worse predictions. So these different insights result in a series of hits on the target, or aiming for something, let's say, for low bias and low variance. But what you need to do realistically is trade off variance or bias. And here we can see that a low bias model with low variances in the quarter of the target will predict correct values on the target. The low bias high variance model will predict values around the bullseye, but with a high degree of variance. Versus a high bias low variance model in that lower quadrant, we're going to have a high bias to a certain location, but low variance. So all your model's predictions will be in a certain area. And high bias at the worst high variance means, well, you're basically everywhere. A common attraction for beginners is to constantly add complexity to a model until it fits very well with a training set. But for now, we'll start understanding this in a machine learning algorithm, or learning about linear regression. So what you might want to do is suppose that you're given a set of red training data. You are now testing data region training data, okay? Now, you may have a simple model like a blue line, and you get a specific error in your training data, and you decide as a beginner, well, maybe I should make the model more complex or more flexible so that we can get all these training points. However, for hitting all those training points, you're going to, your model's going to fail to predict for new test points, which is why we do that train test split. Doing so can cause a model to overfit your training data and, as I mentioned before, cause major errors in new data, such as the test set. So what we're going to do now is we'll look at an example model of how we can see how overfitting occurs in terms of an error using test data. So what we'll do is use a black curve with some noise points to represent the actual shape the data follows. Okay, so we have three images here. First one is X versus Y. And here we have model flexibility as different linear fits. A linear fit, a quadratic fit, or a curve fitting, each becoming more complex, right? So the simplest is just a linear fit. More complicated, quadratic. Then you could have a spline fit. And notice here that the black curve is the truth that the model actually follows. So all the points are just noise around the actual black curve, which is a truth. Now, to evaluate your models and compare the complexities, all you need to do is determine the complexity or flexibility of the model. For instance, the polynomial level of a regression fit versus the error metric, such as mean squared error. Now, as you can see here in the middle plot, we did exactly that. And we plotted for training data versus test data. Now, notice over here to the left, we have a simple model, the yellow linear model. For this model, we have a high error in both test data and training data. And as we get more complex with a blue quadratic model, we begin to reduce the error for test data and training data. But as a result, you start to increase the error in test data, new data. So you want to find the point, you see, This will balance bias with variance. So in this particular case, it's going to be closer to the quadratic fit, the blue point. So you want to balance out the bias and variance of your model to the point where your test data and training data have reached some sort of minimum and grouping together. This is a classic drawing that shows this as a general stance where you have low and high model complexity on the x-axis and some kind of prediction error on the y-axis. And as you move to the left, you get a higher bias but lower variance. And as you move over here to the right, to a higher complexity model, you get a lower bias and a higher variance. So what we want to do is pick a point where you're comfortable with the bias trade-off. You can go to the left of it. You'll start to underfit the data. And then let's go back over to the right. You'll start to overfit the data. So what this means is you're hitting all of those points and your training data and new data is cutting a larger error because of that. Okay, so keep that in mind as we continue using Python for machine learning. Now, of course, this is a bit of that theoretical background. And if you want to look at it more in depth, it's something to keep in mind when you start working with your real world data. All right, my dear friends, thank you, and I'll see you in the next lesson. Well, hello, dear friends. Welcome to the introduction to the Logistic Regression lesson. So in this lesson, we're going to discuss classification problems, how to use logistic regression to solve them, and how to interpret the results of logistic regression to read the confusion matrix. All right, so let's get started. Now, classification is a problem of determining which categories a new observation belongs to on training data. Some examples of classification problems include trying to detect spam for spam, trying to determine if someone is paying off their debts, or even trying to diagnose a disease. For example, trying to find out if someone has cancer. Now, all of the above examples are binary classification, meaning that we have two classes, right? So far, we have seen regression problems in our studies where we only try to predict a continuous value, such as the price of a house. Although the name may be confusing at first, logistic regression allows us to solve classification problems where we try to predict discrete categories. The binary classification rule is to have two classes, 0 and 1. However, we cannot use a normal linear regression model in a binary group. It doesn't fit well. For example, if we look at the graph below, we have a y-axis that represents the probability of belonging to a particular group. Let's go ahead and imagine this example conspiracy trying to predict the probability of repaying a loan. So we'll go ahead and label their loans with a 0% probability of default, meaning they'll 0% likely to repay their loans. And at the top, our probability of repaying loans in full is 1, or 100%. We'll go ahead and mark the x-axis as some sort of paycheck value. So if we go ahead and look at this data, as your paycheck drops, your probability of repaying your loan approaches 0%. However, as your paycheck value increases, your probability of repaying your loan has not approached 100%. Now, the reason these yellow lines are all 0% or 100% is because it's training data. Now, what if this was trade data and we try to use a linear regression model on it? Well, we would have a very bad fit. In fact, we'd have to guess the probabilities below 0%, which really doesn't make any sense. So instead, we can convert our linear regression to a logistic regression curve. And you're going to notice that our logistic regression curve can only be between 0 and 1. And this will be key to understanding classification using the logistic regression curve. By the way, it's also known as the logistic function. So the sigmoid will be key to understanding how to use logistic regression to perform a classification. Now, the key secret to this function is that it can take in any value, and its output is going to be between 0 and 1. So the function of z is equal to 1 over 1 plus e to the power of negative z. Now, the main thing to note here is that it doesn't matter what value of z you put in the logistic function or the sigmoid function, you will always get a value between 0 and 1. So again, if you take a look at this graph, it doesn't matter what value you put in for z. The output on the vertical axis will always be 0, well, between 0 and 1. So this is the key to the sigmoid function. So this means we can take this linear regression solution and insert it into the sigmoid function. And that will look like this. Note here that our linear model follows the basic principle of y equals mx plus b. Here we have a linear model as y equals beta none plus beta 1 times x. So we take this linear model and put it in the sigmoid function. We can finally transform this linear regression into a logistic model. So whatever the value of the linear model output actually is, it doesn't matter. When we put it in the logistic model or the sigmoid function, it will always be between 0 and 1. So it results in a probability from 0 to 1 of belonging in the 1 class. And again, no matter what we put in this horizontal reach, it will always get some kind of probability between 0 and 1 on the vertical axis. So this means that we can usually set a breakpoint at 0.5, and if anything below results below 0.5 or 0.5, that will go to 0 class. And then anything above belongs to class 1. So we're going to transform that 0.5 probability as a cutoff point. So we'll go ahead and do a quick recap overview. See if you can tell me what we've just discussed. Okay, I'll tell you what we just discussed. We can use a logistic function to output values ranging from 0 to 1. And again, it doesn't matter what we put along the vertical axis. We get a value from 0 to 1. So based on this possibility, we will be able to assign a class. Now this makes sense by putting a cutoff point, 0.5, because we want to be able to tell if the probability of belonging to the first class is 50% or less. And then we should classify it as class 0 in our binary classification. Now if our probability of belonging to class 1 is 0.5 or higher, we'll go ahead and assign this new point to class 1. All right, so let's talk about model evaluation and using a confusion matrix. So after training a logistic regression model to classify some training data, you're going to want to evaluate the performance of your model on some test data. So you can use a confusion matrix to evaluate classification models. Now, the confusion matrix, this is a table that's often used to describe the performance of a classification model over a set of test data for which the actual values are already known. The confusion matrix itself is actually relatively straightforward to understand. However, sometimes the related terminology can be a bit, well, confusing. So let's go ahead and examine this example, shall we? So in this case, we have a binary classification problem. So in this example, we'll test for the presence of a disease where no is a negative test, which is false equals 0. Yes is a positive test, where true is equal to 1. Now, what can we learn from this matrix? Well, just straight off the bat, there are 2 possible predicted classes, right? Yes and no. If we were predicting the presence of a disease, for example, yes would mean that they have the disease. No, it would mean that the patient wouldn't have the disease. So the classifier made a total of 215 estimates. That is, 215 patients were tested for the presence of the disease. Out of those 215 cases, the classifier predicted a yes 135 times and no 80 times. So in fact, we already have labeled test data. In the sample, 130 patients have the disease, 85 patients do not. You see that? So we'll go ahead and define the most basic terms. Basic terms are the integers that it specifies. So the odds don't just keep the numbers. And these terms are true positives, true negatives, false positives, and false negatives. Now, if you've done a lot of studies on vaccine controls or disease control, you may already be familiar with this terminology, but if not, we'll review it. True positive, yes, cases that we presume to be illness, and they actually have the disease. So that's TP, true positive. So in this case, you can find it here at the bottom quadrant where TP is equal to 120. True negatives are these places where we know that illness doesn't exist. And again, actually, they don't really have any illness. That's why it's up here in the upper left-hand corner, TN, and that's equal to 70. So that's true positives and true negatives. They do not contain false positives and false negatives. False positives are where we predict yes to have a disease that they didn't actually have. It's also known as a type 1 error. False negatives are where we estimate that they have a disease that they don't actually have. And that's known as a type 2 error. Then we can talk about rates. So the first rate we can discuss is accuracy. And what this really shows us is how often is it true in general. A lot of times when you hear reports on studies, they'll just tell you the accuracy. And the accuracy is calculated by the number of true positives plus the number of true negatives over the total. So in this case, our model is 88% accurate. Then we have the misclassification rate. And this actually answers the question, how often is the model wrong in general? So this will be calculated by the number of false positives plus a number of false negatives divided by the total. So that's 25 divided by 215. Typically, this is the 11% error rate or misclassification rate. So now let's talk about false positives versus false negatives for a nice quick way to remember it, or your type 1 error versus your type 2 error. So remember, the false positives that I pointed with a mouse here, FP equals 15. Yeah, so that's where we guess, but they don't actually have the disease, right? So that's type 1 error. False negatives are what we guessed as no, but they actually have a disease, so this is known as type 2 error. And so, my friends, we can go ahead and think of it as a nice way to remember type 1 error and type 2 error as this funny little diagram. So type 1 error is where you're telling a man they're pregnant. Again, you're predicting, yes, they're pregnant, but they actually don't have any, well, they're not pregnant. The type 2 error is a false negative. So here you're saying to someone that's obviously pregnant that, no, you're not pregnant. So you're predicting no, but they actually are pregnant. And that is a good visual for the difference between a type 1 error and a type 2 error, false positives versus false negatives. And statistics are commonly referred to as type 1 or type 2, instead of their actual names, false positive or false negative. So I hope that's a nice, very useful, and a little bit of a fun reminder of how to memorize these terms. So we'll begin to explore an example of logistical regression using the famous Titanic data set. Oh, that sounds intriguing, huh? We are going to use Python to predict whether a passenger will survive based on features. Okay, dear friends, thanks a lot, and I look forward to seeing you in the next lesson. All right, see you then. Hello, dear friends, and welcome to another lesson of Logistic Regression using Python. So I'm really excited about this lesson because we're going to be working with a huge data set. This is a very famous data set, actually, and it's often a student's first step in machine learning for classification. So we're going to try to predict the classification, survival or death for passengers on the Titanic. And we're going to use a semi-clean version of this huge data set in the data set. The original source is actually from kaggle.com. So why don't we just get started? Okay, my dear friends, if you jump into the machine learning partitions folder under Logistic Regression, you're going to see some files here. These are the test.titanic.csv and train.titanic.csv files. And these are the data sets that we're going to work with. So just go ahead and use these two CSV files that have already been downloaded for you. And the notebook we're going to be using is Logistic Regression of Python. Alrighty then. Now let's go ahead and jump straight into a new notebook. So first up, and as always, we'll get started with imports. I'll do pandas as PD, numpy as NP, and then I'll just go ahead and do my visualization imports. So I'm going to say matplotlib.pyplot as PLT. Likewise, I'm going to import Seaborn as SNS. And then since I'm using this notebook, I'd like to say matplotlib inline. All right, so we're going to go ahead and start making a pandas data frame by reading the train Titanic CSV file. So I'm going to create a data frame called train, and I'll say pd.read_CSV. Actually, I can start typing train, and if I click on the tab here, it'll autocomplete with these options available for me. Okay, so in this case, I want to train_titanic.csv, and we'll run this, and then I'm going to go ahead and check the head of the data frame just to get an idea of what's inside. Yeah, so it looks like we have a passenger ID column, a survived column, and you're going to notice this is 0 or 1. That is 0 if the passenger did not survive, and 1 if the passenger survived. So the passenger class, the P class column, can be first class, second class, or third class. That is, depending, of course, where on the ship the passengers had purchased their passage. There's also the passenger name column, the sex column of the passenger, that is, whether they're male or female. The column here, the age column, of course, is the age of the passenger if it was recorded. And then this SIB, SP column, showing the number of siblings or spouses on board. And then the column par SH shows the number of parents or children on board. And then there's a ticket number column, passenger fare column, approximately how much they paid for the ticket. Yeah, so there's a cabin column, which is the cabin that they're in, if it's known. And then the column embarked. And that's part of the yield, namely C for Cherbourg, Q for Queenstown, and S for Southampton. Okay, so these are the basic columns. And let's go ahead and get started with some exploratory data analysis. Now, most of the time, you got to know, right, we'll have missing data. We will continue to create a simple heat map to see what we've missed most out of our data using Seaborn. So I'm going to go ahead and do this. So I have training data, and if I say is null, or is null, let's see about using this as a method. So I'm going to go ahead and just let me show you what this looks like first, at least what the output looks like. You'll get an idea of what we're doing. So these data frames are huge, right? I've already said that, but basically you get true and false Booleans. So false, obviously, if not empty, or true, if empty. So remember back to that very first cabin, it was NaN. So it was unknown. It was null. So it went ahead and put true there. So with this kind of data frame, I can actually make a heat map. So I'm going to call it sns.heatmap. And then I'll add a few more arguments so we don't get a lot of tick labels. And I'm going to say y tick labels equals false. And I'll go ahead and say C bar equals false, because we don't want to make any real color stick. And then finally, I will pass CMAP as VIRIDIS. So we'll go and see what this gives us. Okay, so be careful with what I've created here. I've created a heat map, right, from these Boolean values. So these are true and false statements. And thanks to this CMAP, every yellow line here is color matching, representing a real point where it is basically empty. So we can now order and check the data from a remote bird's eye view Yeah, so some of the age column information is missing. A lot of the cabin column information is missing. And only one line of the embarked column sequence is missing. So I'd say about 20% of this age data is missing. So I can really use the information of the other columns to fill in the reasonable values for that age column. So I'm looking at the cabin column. See that this data is missing too much to do anything really useful with it at a basic level. So you know what? We're probably just going to go ahead and drop that later. But let's go ahead and visualize this data a little bit more. So we'll come back to the problem of dealing with missing data later, because that's a whole issue in and of itself. So we're just going to go ahead and make a few more plans to do some exploratory data analysis, just, the visual cursory level. So I'm going to go ahead and say SNS set underscore style to white grid. Now, I personally think it looks a little better, as I prefer this style, but to each his own. Now, the first thing that I want to do is just take the number of those who did not survive and the survivors for the classification problem, right? So it's always a good idea to just see the proportion of actual target labels. So now we can do this for a simple count plot. So I can say SNS.countPlot. And then I'm going to go ahead and set the X to survived column. Set my data to train and then go ahead and run it. All right, so as we can see here, I have quite a few more people that did not survive versus the one column which represents survived. Now, gosh, they should make a movie about this, huh? But anyway, it looks like around 550 of these passengers in this data set did not survive. And it looks like about, well, in this particular training set, we have about 350, maybe a little less, that actually survived. So it seems that there are fewer survivors than those who did not survive or died. So we're going to go ahead and do another count plot so that we can see survival with the hue of sex, as it's called. And actually, I can add this hue. So I'm going to say hue is equal to sex. And this is going to add some color. So I can be able to surmise the survival rates by gender. Okay? So I'm going to go ahead and add a palette argument to make this a little easier to see. So I'm going to do rdbu underscore lowercase r. Okay, so now the males are blue, the females are red or light pink, just depending on your monitor. Okay, so for me, this makes it a little easier to read. All right, so looking over this plot, I can say that there really is a trend here, right? So those who didn't survive were apparently far more likely to be males, and survivors were almost twice as likely to be females. And when we look at the factors and coefficients that would cause someone to survive, we will see this trend emerge a little later. So let's go ahead and continue exploring the data by changing this hue to the passenger class. So I'm going to go ahead and call it P class instead of sex here. And for the passenger class, I'll go ahead and remove this palette and just use the default palette. Okay. So again, looking at this, we can kind of tell the trend here with survived versus not survived. And it looks like the people who did not survive were overwhelmingly part of third class or the lowest class. In other words, the cheapest class to buy a ticket into. Don't want to make any political assertions. This is just data. The numbers tell a story. So it seems that the ones who survived were leaning toward the slightly higher classes, 1 and 2. Now, we will also have to see how many people are actually in the passenger class or per passenger class. But we'll be doing that analysis. So let's go ahead and get an idea of the age of the people on the Titanic. So to do that, I can go ahead and do a distribution type plot. So I'll just go ahead and say SNS.distplot and pass in the age column. Now remember, distplot only takes an array of values. So for now, I'm going to go ahead and say drop NA because I don't want these to break my distribution plot. Also, KDE equals to false, because because I just want to see the histogram of these values. And let me set the bins to something a little higher, like 30. All right, so let's run that. Okay, so we have something interesting here that almost appears in the model distribution with quite a few passengers between 0 and 10 years old. So there are quite a few children in this area. But after that, you can see that somewhere out there is starting to get an average age towards 20 or 30. So it's quite possible maybe it's skewed towards younger passengers, and the older you get, the less representation you have on board. Okay, so let's go ahead and show you another way that you can dist plot. If you weren't a big fan of Seaborn, you can always do that. I'm not going to judge. You can not be a fan of Seaborn, but you can always do something like dot plot hist directly in the age column, and Panda's own visualization can do this for you. So here we'll say bins to something a little higher, like 30. Again, and we'll get a similar looking graph. Okay, so let me go ahead and go back to the Seaborn real quick. And let's go and explore some of the other columns just to get a reminder of what those columns are. I want to go ahead and call info. So this is the call info method. Okay, so we've already checked out the survived column quite a bit. We've seen the P class, the sex column, the age column. Let's go ahead and explore that SIB-SP, and that was the number of siblings or spouses on board. So let me go ahead and do an sns.countPlot. Set x equal to SIB-SP. And my data that I'm going to use is the train data frame. Okay, so now looking at this plot, I can basically immediately tell that most people on board did not have either children or a spouse on board. So that's interesting. If we look at the second most popular option, which is actually most likely to be probably a spouse versus just having a single parent with a child on board. So according to those numbers, pretty much it makes sense that you have a lot of single people on board, yeah? Probably those are men in the third class, maybe. And after that, you have the second most common type of passenger in our data set. Now, this is some of the just one either sibling or spouse, and that's probably going to be their spouse of couples on board. Okay, so we haven't explored the other columns yet. One is the fare column. So let's go ahead and take a look at how much people paid as a distribution. And we're going to go ahead and do this with pandas. So I'll say train fare. So now if we take a look, keep in mind that these, well, they're basically just the prices that they paid for. Now to call a histogram, I'll say .hist. Let's go ahead and run this and we'll see what we got. Okay, so we immediately see that there is a fairly wide range of values. Most distributions seem to be somewhere between 0 and 100. So to get some more detail, I am going to increase my bins size to 40, and then we can also kind of stretch it out, passing in fig size to maybe 10,4. Okay, so it can now get a higher distribution or higher level of detail in this distribution, to be more precise. Cool, so it seems that most of the purchase prices are between 0 and 50. And again, it makes sense to distribute these because they're cheaper tickets, because you can already see most passengers are actually in this cheaper third class. And this isn't me, this is just the way it was in 1912, so these prices haven't been adjusted for inflation. So let me just go ahead and I'll show you an example of how we can make this type of plot with cufflinks, if you really like interactive plots as much as I do. All right, go ahead, twist my arm. So we could say import cufflinks as CF. And then we tell cufflinks we want to work offline. Then we go ahead and essentially do the same thing. So grab the fare column of a train, and then we just say iPlot to see this in our plot, and say kinda equal to hist. You can specify more bins, and then let's see this run. So I can go zoom in and check these bins myself and add more bins. So I want to put 50 bins. Zoom in and see where I am most interested in and use this. Okay, so my friends, there are many things that you can do with Python. Very powerful language, and there are many great libraries for it. Okay, so I'm going to go ahead and comment this out right now. And you know what? We're going to end this lesson here because we finished our exploratory data analysis. Okay. So to recap, we went ahead and kind of explored the data without really knowing too much, except with our historical lens, of course. Now we saw the distribution of fair prices. We saw the accounts of siblings versus spouses on board, made an assumption that most of them were probably single based off of this count or just had one spouse. We went ahead and checked the age distribution. And we also looked at survival and passenger class and survival and gender. So again, we can see that mostly men are in the non-survival group and mostly female are in the survival group. And then we found that we had quite a bit of incomplete information, and we wanted to find out how we can deal with the age column and this cabin column, right? So we'll continue in the second part of this series of lessons and discuss how to deal with missing data. All right, my friends, so thank you to everyone involved. I'll see you in the next lesson. Well, hello, my dear friends, and welcome to the second part of Logistic Regression in Python. So in the first part, we focused on exploring data through visualizations. And in that exploration, we actually found that we have, I would say, to categorize it, quite a lot of missing data. But that shouldn't stop you. What we want to do now is shift gears to cleaning our data. So cleaning our data will enable us to transform our data into an acceptable form for our machine learning algorithms. So we'll go ahead and go back to the Jupyter Notebook where we were last time. Okay, so here I am in Jupyter Notebook, and if you remember from the last time, we used a little trick with the train is null method. We did SNS heat map to quickly create a map visualization of where the missing data is located. But instead of removing all the missing age data rows, we want to fill in the missing data for the age column. Now, of course, one way to do this is to enter the average age of all passengers. This is known, yes, this is a technique. It is known as imputation. And that means you can just take the average age and fill in the missing values with that average age. However, we could actually be one step smarter in this regard and check the average age by passenger class. Let me show you how that works. All right, so I'm going to scroll down, and I'm just going to go ahead and create a box plot using Seaborn, with X equal to P class column and Y equals to the age column. And it will be equal to train in my data. All right, so let's go ahead and run this and take a look at our box plot. So what I'm going to do is set this to plt.figure. Fig size is equal to. And let's go ahead and make this, let's say, 10 by 7, so it's a little bit bigger. Okay, so we can now zoom in on the center points of the box plot. So here, split by class, we can see that wealthier passengers in first class and second class actually tend to be slightly older than third class passengers. Now, you might think, okay, well, maybe that makes sense because, well, it could take age or time to accumulate wealth, reach material wealth of the first class or whatever. So if you have enough time to accumulate enough wealth, you would probably be older, more likely to be in first class, yeah? Well, then what we can do is use these average age values to determine the age depending on the passenger class. See where we're going? So now if you wanted to, you could create an entire model to try to predict age based on all the features. So you could go ahead and use the sort of simple imputation, which is a little better than just imputing the average age. So why don't we just go ahead and create a function to implement this function, and you'll see what's going on. I'll just say impute underscore age, and this will take an argument called COLS inside. And then I'm going to go ahead. Yeah, so what I'm going to do here is essentially say age is equal to cols 0. So the first item here. And then we'll say p class is equal to cols 1. So the second item at index 1. And what I'm going to say here is if pd dot is null of age, and then I'm going to have some if statements here. If p class is equal to 1. So one of them in the first class. And I'm going to go ahead and return the average age for passengers in the first class that occurs at 37. So if you want to get the exact value, what you could do is just go ahead and actually get the average by class using pandas. Or if you wanted to, you could create a box plot using Plotly and just do it that way. So here I'm going to say return to 37, and then if the p class is equal to 2, meaning in the second class, I'm going to go ahead and say return 29. And then finally, else, meaning they're not in first or in second class, but they still have null for age. And I'm going to go ahead and say return 24, which is the average value here for the third class. And then I'll say else. If my value is not empty, I will return their age because I already know. Okay, so that's the function, and we're going to go ahead and apply that function. So I'm going to say train, age is equal to train. And now I'm going to pass in age and the p class column. So a list of these columns and dot apply. And I pass in the name of the function I want to apply. And then say x is equal to 1. So I want to apply this across the columns. Yeah, so it ran correctly. Now let me go ahead and quickly explain what's really going on here. Are you ready for that? I'm sure you are. So I've created a function here that takes an argument, cols, and notice here that it actually grabs, based off my index values, the age and p class, and I'm able to do that because I'm using that apply these two columns. And then I'm going to say if pd dot is null, that age. So at that particular point, then we check by passenger class. If it's first class, we return the average age for the first class passenger. If it's second class passenger, return 29. Otherwise, if it's third class, return 24. And of course, if they're not a null, then we actually know the age and we just return that age. And then I went ahead and I applied that function to these two columns here. And then I said axis equal to 1 to apply it to the columns. And now we can go ahead and check the heat map again. So I'm going to say Seaborn or SNS.heatmap. Train dot is null. And set ytick labels equal to false. And then I'll just go ahead and set cbar equal to false. So if we run that, we get this color mapping scheme. And what I do is I set my color map to Veritas because, well, it's just easier for me to see. Okay, so you see how it looks like we no longer have any missing information for the age column. So that means we've successfully placed values that are reasonable estimates for people's age, and we get that data from other classes. Now, the issue we have now is the cabin column. And to be honest, there are just way too many missing points to do something, well, that's useful for that column. What you can do is maybe try to create a new feature that tells us that we know 0 or 1 for the cabin. But again, there's a lot of missing information here. It's easier to go ahead and just drop that cabin column. So in order to do this, I'm going to say train dot drop cabin and state that the axis equal to 1. And then I'm going to go ahead and say in place is equal to true. And if I check out train head, do you notice that when you go ahead and scroll, you're going to see that there is no cabin column anymore. And if I go ahead and run it, now pay attention to this again. Now we only have that missing value embarked. And since this is essentially one row of some missing information, or, one or two rows, so I'm going to go ahead and drop more missing values. So I'll say train.drop NA and set in place is equal to true. So now I should have no missing values. So I'll go ahead and run this one more time. Okay, so you see how everything now has a single color. Nothing's missing, and that means we're good to go. All right, so we've taken care of the last step of cleaning our data, and that deals with the missing values. So we went ahead and we filled in some missing values, and we went ahead and dropped some other missing values. Yeah, so now what we have to deal with is the categorical features. We'll use pandas to convert the categorical features into what's known as the dummy variable. See, otherwise our machine learning algorithm cannot take these features directly as input. So that's all to say, let's do something like this. If you see that the sex column here, we categorically have a male or female feature, right? Well, a machine learning algorithm isn't going to be able to take in just a string of male or a string of female, so we'll have to create a new column. In short, to encode this information in a way that a machine learning algorithm can understand it, it's necessary to implement a method that's known as the dummy variable. Something similar can happen inside the embarked column. So we'll have a look at the embarked column here. It's just a letter representing a city. And again, a machine learning algorithm won't be able to just take that letter and immediately know what to do with it. So they'll need something in a dummy variable format, which is going to indicate a 0 or a 1 with a column as an actual value for a particular city. All right? So let me just continue to explain this in a little bit more detail by showing you some of the examples of how we can do this with Panda. So I'm going to go ahead and say PD and use the get_dummies method. And of course, you can go ahead and click on the Shift tab, and you want to explore this method a little more. Actually, this method is basically just going to convert categorical variables into values known as dummies, or otherwise known as indicator variables. I just like saying dummy, I guess. You big dummy. Anyway, we're going to pass in the column that we want to convert. For example, the sex column, male, female. If we do that, pay attention to what we pull out. Now, this has a little problem. One column here is a perfect predictor of the other column. So if our machine learning algorithm feeds both columns, for example, if the machine learning algorithm sees 0 in the female column, it will perfectly predict that it will be male. You follow? So this is a problem known as multiple linearity. It's basically going to mess up the algorithm because a bunch of calls will be perfect predictors of another column. So yeah, that's something to know because we've got to avoid it. And in order to avoid this, what we got to do is, as another argument here, we are going to go ahead and say drop first equals true. All right. Then we'll go ahead and drop the first column. And now this is exactly what we want to feed into the machine learning model algorithm as a column. Now we're going to go ahead and equate this to the sex column. Sex column is the data frame of whether this person is male or not. And now we're going to do a similar thing for the embarked column. And we create a data frame called embark. And we said embark equal to pd.getDummies train embarked. We'll go ahead and say drop first is equal to true. Now run this. And then I'm going to go ahead and check out the embarked data frame. Just ahead of it. And look here, it went ahead and dropped the C column, and now I have indicators of Q and S. But notice one call or all columns are not perfect predictors of each other because it went ahead and dropped that C column. Now what we can do is say train equals pd.concat, and we'll just use concatenation to add these new columns to our data frame. So pass in a list of the data frame to concat, and we train and then the new sex and embark data frames. And we'll say axis is equal to 1 because we want to add them in the new columns. And we'll check out the head of train. And we'll get something that looks like this. Yeah, so let's just have a look at the top 2 rows here. Yeah, and then we'll go right. Notice that these new columns, male, Q, and S, so these will be the pillars to replace our machine learning algorithm. These are the indicator or dummy variables. So what this means is we don't really need these other columns anymore. So we no longer need this embark column because we already encoded it in Q and S. Likewise, we don't need the sex column anymore because we've coded it into this male column. What about the other columns? These are things like ticket column, name column. There's really not much information we can use there. Of course, you could try feature engineering and new features like grabbing the first letter of the ticket or the title of someone's name if you want to. That's always a fun exercise. We're not going to do that here, but you can go ahead and do that on your own. What we're going to do is go ahead and just drop the column. So that means we're not going to use it. So we're going to say train.drop, and I'm going to pass in the columns. And I'm going to use sex column because we already coded that into the male column. Likewise, for the embark column, I'm not going to use that column because it's already encoded in Q and S. And I'm not going to use someone's name because really there's no way to easily pass that into a machine learning algorithm. 10 points extra if you do, but I'm not. So maybe we can feature engineer some stuff off of that. And no. It actually gets quite complicated since we're dealing with text data. Not really the focus of the course here. So what we'll do is fill in the ticket column and drop, because there's really no easy way to grab information from a machine learning algorithm with that either. All right, so finally I'll say axis equals 1, because I want these to drop from all rows of the columns, and set in place is equal to true for this situation to be permanently valid. Okay, so now let's look at the header of our data frame. Cool, this looks perfect for a machine learning algorithm. All data is numerical. Everything is together. So now our machine learning algorithm works perfectly. So the last thing that we want to look at, this first numeric column, passenger ID. Notice that this passenger ID is actually just an index starting from 1. So let's go ahead and check the tail of the data frame. Yeah, exactly the same thing, just an index starting at 1. So that just means that even numerical ones are essentially not useful for predicting whether passengers will survive based solely on their position indexes, right? So yeah, we'll just go ahead and say drop pass in passenger ID. And say axis equal to 1. And we'll say in place equal to true. So let's just go ahead and check the head of the data frame one more time. Okay, so now let's take a quick last look at the columns. You know, it never hurts to double, triple, or whatever check, just to make sure everything is fine. And we have the survived column, which is 0 or 1. And that's good because that's our label column. We have the P class column as the numerical indication of what class they were in. We have the age column of how old the passenger was. We have the SIB SP column, how many siblings or spouses they had on board. We have the PAR CH column, how many parents or children they had on board. The fare they paid, whether or not they were male, whether or not they embarked that Q or not, whether they embarked that S. The interesting thing to note here about the P class column is that it is actually a categorical column, meaning it can only have 1, 2, or 3 different categories. That means that we could have also done pd.getDummies on that column. But you know what? I'm just going to leave that to you. Why don't you pick that up as an extra exercise to do? after you've already run the model with it as a normal column just by itself. And this is because I want you to explore the differences between leaving it alone as 1, 2, 3 columns and using the pd.getDummies of the separation of these categories. And then you'll be able to discover on your own how a machine learning algorithm will react to a column treated categorically against one that is a continuous variable. Okay, dear friends, that's it for part 2. So what we did in part 2 is go ahead and clear the data, reading incomplete data filled with some other data. We also learned how to use the getDummies function to create and deal with categorical columns. So coming up next, the final steps, where we're actually going to create and train and build our machine learning classification model using logistic regression. All right, my friends, thank you to everyone involved, and I want to see you in the next lesson. Well, hello, dear friends, and welcome to Logistic Regression with Python. This is part 3. In part 1 of this lesson series, we did some exploratory data analysis with some visualizations. In the second part, we cleared the data by handling categorical variables and missing data. So now in part 3, we're going to train and use the model to predict whether a passenger will survive on the Titanic. So let's go ahead and go back to the notebook that we started last time. Okay, so here I'm in the notebook. Here we have the data set. So one thing to note here is that if you go back to your folder, you'll notice that there is a test_titanic.csv file and a train_titanic.csv file. So I'm going to go ahead and cover this training set here, or train it as if it was all of our data. So I'm going to go ahead and review train test split process. What you can actually do is do the same cleaning on the test.csv found here and use it as your test set. Now, since I actually have 2 separate CSV files, in order to go through the process of using scikit-learn train test split, I'm going to go ahead and treat this train data frame as if it was all our data. Okay, so let's go ahead and see how to do this. First thing that we have to do is split our data into X and Y. Notice that Y is the column from which you are trying to predict the actual label. So in this case, that's going to be the survive column. So I want to predict a 0 or 1 in that survive column. Everything else, just going to be the features. So I'm going to go ahead and say X is equal to train.drop survived, and axis is equal to 1. Now I can go ahead and say from sklearn.model_selection, import train test split. And then there I can use the tab for autocomplete. And what I like to do is say train test split. And if you shift tab in the Jupyter Notebook, you can see the documentation stream. Now scroll down a little bit until you get to the example. And you can just grab this, copy and paste. So I'll copy that. And I'll paste it into replace that and put it now all on one line. Okay, so here you have my X train, X test, Y train, Y test. And I'm doing train test split. I'm going to go ahead and set my test size to 30% and set my random state to 101. Now, of course, like I said earlier, you don't need a random state, but if you want your results to match mine, boom, just put it in as 101. All right, so let's go ahead and run this. Excellent. Now we have data for X test, Y train, Y test, and X train. So now the next step is to actually train and predict by creating a model. Now for logistic regression, we'll go ahead and grab this from the linear model family. So I'll say from sklearn.linear_model import logistic regression. And we can go ahead and run that. So for the next thing, what I want to do here is create an example of the logistic regression model. So I'll just go on and create logistic regression. We'll go ahead and call our model log model. And the next step is actually training the model. So if you do Shift Tab here, it will give you some more information about the various parameters you can add, but we'll just go ahead and say .fit xtrain and the y_train and run it. All right, so now we're going to make some predictions using this, our X-test data set. So that means we'll go ahead and say predictions equals log model.predict, and then just pass the X-test because we want to predict values off of that X_test. Perfect. So that's it. If you don't count the train test split, we can actually create a model, fit a model, and predict a model in just 3 lines of code. Now, this is actually very reflective of real-world analysis and machine learning building process. But a lot of times, most of your work as a data scientist is actually going to be cleaning data, getting that data into an acceptable form. In other words, here in a machine learning algorithm. So the machine learning algorithm libraries that you'll be using are actually sufficiently complex and abstract enough that the process of building them will actually be quite simple. So that's why I say most of your work will be reflected in the cleaning data set. Okay, so now let's go ahead and evaluate our model. For classification tasks, scikit-learn has a really nice classification report you can use. You can say from sklearn.metrics import classification report. And the classification report will basically tell you your precision, your recall values, accuracy, the F1 score, and some others. And that way, you don't have to get busy reading a confusion matrix yourself. So I'm going to go ahead and say print classification report, and then you pass in your true values y-test, and then your predictions. So run that and report back the precision and recall for each class, as well as the average total and supporting cases for it, besides the F1 score. Now, if you don't want the classification report and you want the pure confusion matrix, sklearn metrics has that too. You can say from sklearn.metrics import confusion matrix. And you can say confusion matrix and pass in the same thing, y-test predictions, and you'll get the actual confusion matrix to evaluate your model that way. Now, in that way, in case you really want to compute a very specific value, you can do it straight from the confusion matrix. Okay, so considering we're dealing with a smaller data set by splitting our training data instead of using the train and test CSV, these results are actually not that bad. However, you may want to explore other ways to increase your precision or recall or accuracy. So what you can do, actually there's a couple of things you can do. Maybe just try using the entirety of the training set versus comparing it to the test CSV after you repeat the cleaning process for the test CSV file. Other things you can do are more feature engineering, such as trying to grab the title of the name. So in other words, to treat that as a feature, like Dr., Mr., Mrs., you know, the title. And maybe the cabin letter could be a feature as well. Also, the ticket column might have some information for you to do. So go ahead and continue exploring this project as you see fit. There are lots of things you can do. In fact, there's some more information at kaggle.com and how to get started with doing this sort of analysis with Python. And you'll get very, very familiar with it. You'll get so adept, you'll be able to come up with your own methods. So go ahead and check it out. Kaggle's link is available in your notebooks. Now, you will see when you examine that they usually use a random forest machine learning algorithm. But since we haven't learned about tree methods quite yet, you might want to hold off there. But for now, I hope you've enjoyed this project, because coming up with the next lesson is going to be your actual project exercise. You're ready for it, don't worry. All right, my friends, thanks again, and I'll see you in the next lesson. Well, hello, dear friends, and welcome to the Logistic Regression Project Exercise Overview. So here we're going to go over the notebook for the Logistic Regression project. I'm going to go ahead and show you where you can find it. I'll just jump into the notebooks now. And okay, so here I am under the Logistic Regression folder, under the Machine Learning Sections folder, and there you will find a notebook labeled Logistic Regression Project, and another notebook labeled Logistic Regression Project Solution with, guess what, solutions for the project. So we'll also be using this advertisement.csv file, and this will be the data source for our project. So let me go ahead and quickly explain the Logistic Regression project. So in this project, we're going to be working on some data underscore of underscore add. And data underscore of underscore add indicates whether a particular internet user clicks on an ad. Some people might say whether they want to or not. So we're going to try to create a model that will predict whether they are going to click on an ad or not based on the characteristics of that user. The data set also contains various columns and attributes such as age of the customer, income of the customer, the topic line of the advertisement, is the consumer male or not, which country do they live in, etc. Okay? What you are going to do is go ahead and go through the data, import the libraries that you need, do some exploratory data analysis with some visualizations, and then toward the end, what you're going to do is actually do the logistic regression. So that means that you're going to do a train test split, train the model, and browse a classification report. Okay, dear friends, that's it. Enjoy the project, and I'll see you in the next lesson. Well, hello, dear friends, and welcome to the Logistics Regression Project Exercise Solutions. And hopefully you have gone through the project and are just here to congratulate yourself because you want to make sure that you've done everything the way that we've taught you. Well, we are going to go over the solutions of the Logistics Regression Project, but we'll have to see how you do. So we'll go ahead and jump into the notebook to get started. And as you can see, here I am in the notebook, and I'll go ahead and start the missions. So the first thing that you want to do is import several libraries. I'm going to go ahead and import the ones that we usually import, NumPy and Pandas. And I'll also import the visualization of libraries that we use, such as matplotlib.pyplot as PLT. Import Seaborn as SNS. And then matplotlib inline. This way I'll be able to see the visualizations in my Jupyter Notebook. So we want to read the advertisement.csv file as data underscore of underscore add. You can do that with pd.read underscore CSV. Now we want to check the header of data of add. We can do that just with the head method, and we get these columns back. All right, so here we have the columns of consumer time on the site in minutes, customer age in years, average income of geographical area of consumer, average minutes a day the consumer is on the internet. The headline of the advertisement, that's the ad topic line. The city of the consumer, whether or not the consumer is male. The country of the consumer, timestamp column, which the consumer clicked on an ad. Okay, so next we want to use the info method and the describe method on the data of ad. So you can go ahead and just say data of ad.info, and it returns back, 1,000 rows, 10 columns. Then if you want a statistical description, you can just go ahead and say data of ad.describe, and you can see some statistical information about numeric columns. So go ahead and continue with some exploratory data analysis with some plots. So we want to, and we create a histogram of the age column, and you can just call directly age column.plot.hist, or even just .hist, and set bins equal to 30, and let's check it. Okay, so here you see a histogram of the age column, apparently a fairly normally distributed species around the age of 30, 35 years old. It's a little hard to say. right, so the next plot, we want to do a joint plot showing area income versus age. So we'll go ahead and explore that. You can just call sns.jointPlot. So on the x-axis, we want age. So I'll say x equal to age. And on y, we're going to say y equal to area space income. And then we'll say data source equal to data of add. And then we get this joint plot that appears like this. So we can kind of see the relationship between the area income versus the person's age. Yeah, it's a little scattered, but it looks like there may indeed be a trend that you start earning once you start getting into your 20s. That kind of makes sense. Then as you get a little older, it looks like your income perhaps starts to rise. I guess that's what everybody hopes. But as you get even older, even towards retirement, either you start getting no income or, well, that source kind of drops. Okay, so we can go ahead and take a look at a joint plot showing the KDE distributions of daily time spent on the site by age. That's going to look like this, and it's going to show you how it'll do that. So let's say sns.jointPlot. So we want to pass in age as x, and on y, we want to go ahead and say daily time is spent on site, which is the name of the column. And then we're going to say data is equal to data of add. All right, so let's go ahead and take a look at this. Okay, so if you notice this, if the type's not specified, we get a scatter plot again. So I want to go ahead and say kind is equal to KDE. So here I'll take this nice KDE diagram, and if you want to, you can go ahead and set the colors. You can say color equals red, and that way you see the distribution red. All right, so now we can create a joint plot of daily time spent on site versus daily internet usage. So you can say sns.jointPlot and say x is equal to daily time spent on site, and y is going to be equal to daily internet usage, where data is equal to data of add. So now let's go ahead and explore this a little. So what does it look like? I'm just going to keep the colors their default blue. Now it looks like we can definitely see two clusters here, right? Your daily internet usage increases, and consequently daily time spent on the site increases. So you tend to belong to this cluster here. This paired diagram looks almost like a circular pattern, huh? And then what we can do is, in order to explore it a little further, let's just do this joint plot for every single numerical column. So let's go ahead and do that with an sns.pairPlot, and we want to pass in data of add. So now we also want to say hue defined by, clicked on the add column. And I'll go ahead and run it. Now keep in mind that a pair plot may take a while, depending upon how large your data set is. All right, so there are default colors here, and if you want to increase the size, you can just zoom in on this, or just notebook or style, whatever you like. All right, so in fact, we can see quite clearly certain relationships between things like age, income, or daily time spent on the site, or whether they click on the ad. And of course, if that piques your interest, you can go ahead and discover that on your own. So what I'm going to do here is move on to logistic regression. Now, all I want to do is split the data into a trained set and a test set using the train test split. And to do this, we'll say from sklearn.model_selection, import train test split. And then we can always say train test split. We can do shift tab. I always like to scroll down to see the samples. And you can just copy and paste from the sample. Makes your life a little easier. And then we can go ahead and say X and Y. Test size going to be 0.3. I'm going to set random state to 101. And you'll get the same results if you're following along now. So what we want to do is set X first, and that's going to be the data of add. And if we look at the data of add again, we go ahead and create a quick data of add.head. So let's look at the first line and see what we really want to pass. All right, so I want to pass in actually all numerical information because it looks good. All right, so then the columns that I want to drop are some string information like country or city or even add subject line. I also need to get something from the timestamp column so that it is not missing. So we'll go ahead and just drop that as well. So let's go ahead and just grab the columns that we're interested in for data of add as features. That's going to be the daily time spent on site. Next column we want is age. Also, we'll take the area income and the daily internet usage column. And whether or not that person is male. And that should do it. All right, so those are the columns that we're going to be using. And then for a Y, this will be our target column. So Y is equal to the data of add. And from this data, we can get the click and add column. Okay, so now let's run the code cell. Yeah, sure enough, they look good. So this means that we can train the logistic regression model and fit it to the training set. So I can go ahead and say from scikit-learn.linear model import logistic regression. Okay, so now we can say log model. Go ahead and instantiate logistic regression. I'm just using tab here, and I'll go ahead and fit that to xtrain and ytrain to my training data. So I've created my model. Now I can predict values from it. And I can say the predictions are equal to the log model, the point predicts, and I can pass in my test data. All right, so I'm ready to create a classification report. So I'll go ahead and do that first. I'll say from sklearn.metrics import classification report. And don't forget, we should measure also so that we can do the confusion matrix. And I will say print classification report and pass in Y test and predictions. And you can do the same thing if you want to print confusion matrix, just pass in Y test and predictions. So this gives you a bunch of information. In this case, it looks like we're actually doing pretty well. We're getting around 90% on the precision recall, 93% around for accuracy. Yeah, so it turns out we actually have a few mislabeled spots that aren't bad given the size of our data set. Now you can also clearly see that the blue and the green data for some certain features are here. It is actually quite separate. So this is a good indicator of some things. I know you know what. Don't worry about it, though. I hope you enjoyed the project. It should have been pretty straightforward, but, some of the instructions were deliberately left a little ambiguous. So, you'd actually have to refer to the lesson, especially some of the things like the splitting of the data were left as a single line to split the data, even though it involves multiple steps, right? Choosing the X and Y values, stuff like that. But I know you got it as soon as you get more comfortable with it, especially with scikit-learn and Python's machine learning. It's just going to be so natural. You could do it in your sleep. You will be doing it in your sleep because I dream about this stuff. Okay, so thank you again, and I hope to see you in the next lesson.